Okay, in time dilation, we're going to get started right now. So, I'm Margot Seltzer, and it is my pleasure to welcome you to this joyous event. Now, I'm sure that many of you are sitting here going, now wait a minute, you told us this was sold out, and look at all these empty seats. So what's with that? And what's with that is that we have over 100 students registered. Okay, how many of you remember what time you started classes when you were students? Yeah, okay, so we expect that they will be trickling in throughout the day, and we will, in fact, have all these seats full at some point. So our goal today is to keep things fast-paced and moving along and give you a view as to the breadth of the amazing things that the students of Harry have done. So on that note, I'm going to start with 4 groups to thank, 1 story, and then I'll turn it over to our first speaker. So first, I would just like to thank Frank Doyle, the Dean of Cs, and David Parks, the Area Dean for Computer Science, for supporting this event and making it happen. Thank you. And for those of you who haven't been around Harvard in a while, if we were any other institution, Area Dean would be called Department Chair, but because we're Harvard, it's called Area Dean. The second group of people I would like to thank are all the folks who made this event happen. So if you see the folks working the table, or Susan Forrest, who's our event planner, or Kimia and Gabriella, they really made this whole thing happen. So I just get to pretend that I did things, they did it all. So thank you to all of you. And the third group I'd like to thank is all of you people for coming and making the time to share this with us. So welcome. And finally, okay, this is the audience participation. Who's the last person we need to thank? Harry. Thank you for giving us an excuse to throw a fabulous party. So in the spirit of that, I would just like to share one of my favorite Harry Lewis stories. So one of the reasons we all love Harry so much is because he knows us not only as a student in the classroom, but as a person outside the classroom. And this became quite clear to me when, as a senior, we were chatting, and I said something about maybe someday wanting to go to graduate school. And, you know, Harry, in his ever-supportive fashion, said, you know there's no Harvard band in graduate school. Now, it turns out, as Harry often is, he was right, because I went to Berkeley, and there was no Harvard band at Berkeley. But what he didn't tell me is that you can then come back as a faculty member and be the advisor to the Harvard band forever. So, call out to all my bandy friends. On that note, I'm going to turn it over to our first speaker, Marty Chavez, who's giggling wildly. I've known Marty for about 30-some-odd years. And in addition to all the amazing things he's done, you know, in the field and stuff like that, which you can read about, he is also now a member of our Board of Overseers and on our visiting committee, and has been a really great friend to Harvard CS. So on that note, Marty, take it away.
As Harry told me about being a Board of Overseers member, the single best thing about it is that now, after decades, I'm finally Harry's boss. And so, I just want to share a few stories about Harry, and we all have so many of them, and connect them and show the profound influence that all of them had in my life. Now, they might seem random, and that's part of the joy of it. So, CS11. I was a teaching fellow for Harry in CS11, which would have been, I think, 84? It's a long time ago. And I remember something that Harry gave us the license to do way back then, which was if we received a programming assignment that had an inline constant, we were at liberty to write F at the top of it and hand it back. And I never really thought so much about that until many, many, many years later in my career. Some of you will know this story. We had some software that unfortunately put in an order to buy nearly every listed option in the US market for $1. And when we traced it all back to how that actually happened, there it was. Someone had actually typed the evil line of code, price gets 1. And that led to all of these consequences. And so it was something that seemed abstract and pedantic and yet so important. Years later, when I came out, actually after telling my parents, for whatever reason, Harry was almost really the next person that I wanted to tell. And by then, he was on a different coast. And I remember he came out to San Francisco, and Harry, always being up for it, wanted to go to a really cool gay bar in San Francisco. And so I found one, and there were Harry and I at this bar talking, and suddenly I noticed a very odd thing. It was really one of the fastest hand gestures I've ever seen in my life. But just as we're talking, in conversation, Harry's arm flashed out. He grabbed an ashtray from this gay bar and put it in his pocket. Well, anyway, I just had to share that. So I hope you still have the stolen ashtray. He wanted to memorialize the occasion, and so one top tip from Harry on that one is never pass up an opportunity to steal a fabulous ashtray. And so then, about a year after that, Harry had revised his legendary textbook, and I remember this touched me in such a deep way. He sent me a copy, and he said that, thinking of me, he had decided to put our mutual favorite gay guy on the cover of his book. And of course, that's Alan Turing. And it really was through Harry and through CS121 that I discovered this love of discrete mathematics I didn't know I even had. I always thought of myself as the ultimate applied guy. When it came time to put together my Stanford PhD committee, it was really important to me to have someone who would be tough and challenging for me, but someone whom I loved. And there was really no doubt in my mind that I wanted Harry to be on my PhD committee. An immense hassle, actually, to do this bi-coastal thing, but something for which I'm totally grateful. A couple years after that, there was an interesting email from Harry. And in this email, Harry said, "Hey, Marty, you know, it seems like there's a lot of your brothers and sisters who've come through this place." And I said, well, as a matter of fact, yeah, there has been a few. There's been 5. And one of the things, a lovely thing about Harry, is that he looked after all of us, even those of us who were misled and were not actually computer science majors. And so one thing led to another, and Harry thought that this was really worth some energy. I actually hadn't thought about it much, and one thing led to another, as really only Harry can do. And the next thing I knew is I found myself on the set of the Today Show. And the Today Show being broadcast live from Adam's house on the occasion of my baby sister's graduation. And I didn't really connect all the dots, and you can only see how things lead to other things serendipitously when you look back at all of it. But that was really my first episode of media training, and that was something that served me incredibly well ever since then, because there I was on the set of the Today Show, and Harry's on the side, and I'm there with my mom and dad and all my brothers and sisters, and Matt Lauer in front of an audience of, I don't know, it turns out tens of millions of people watched that thing, had said, you know, Marty, it sounds like your mom was kind of a monster. What was it like growing up with all of that? And this is one of those things where my first thought was, I can't believe Harry got me into this. But then my next thought was, well, there's got to be something that I can say in this moment. And that was, well, you know, she was tough, but I realized, looking back at all of it, that no two people beyond my parents have ever done more for anybody, and it might have seemed rough, but it was all for a purpose. I remember then traveling in part with Harry through a valley of darkness that I would say that the label of that valley of darkness was Larry Summers, and that was and Harry had his version of it. I had my version of it. I think as we came out the other side, certainly in terms of the financial governance of Harvard and the endowment, the university is a better place as a result. Now, here's one thing I wanted to share with you. I think there might be some recording, so I'm going to have to be a little bit judicious on this one. But one thing that never occurred to me was that Turing decidability would become a topic that I would address in a profound way in a room full of financial market regulators in London. You wouldn't really think of these things as being connected, but in part of the post-financial crisis cleanup, there was a profound idea floating out there, particularly in the regulatory community, that wouldn't it make the system better if we would just write documents about all of our code and then have people verify that the documents were perfect, and therefore the code would be perfect and it would never have errors. And so I remember saying, well, that was a lovely idea. It turned out to be an impossible idea, and something that, in fact, one of their countrymen had demonstrated: do not attempt to decide the undecidable. And so these concepts of complexity theory and decidability, things that one would think of would be quite abstract, turn out to be so important in the real world, and one wouldn't want to take any false comfort from attempting to decide the undecidable just because it sounded intuitively like a good idea. The last moment I want to share with you is something that gets me quite emotional. Somehow Harry's always known what was going on in my mind, and there was a time, I don't know if you even remember this, Harry, 10 years ago, really apropos of nothing, I was at a pretty rough point in my career. It was not quite 10 years ago. It was 8, and it was in the time of the financial crisis. Do you remember this? And I was not a happy camper, I think would be an understatement. And for reasons I don't completely understand, you got on a train and you came to New York, and you said you had only one thing that you wanted to share with me, which was that I was standing not even near the middle, nowhere near the end, but really absolutely just at the beginning of my career. And this is at a time when I was exhausted and low and thinking that I was done and just wanted to get a little shack somewhere on the beach and stare at the ocean for 10 years. And somehow, just your saying that completely changed my perspective on life, the universe, and everything in a way that I think no one else could have done for me. And so, right after those tiger parents of mine, no one in my life has done more for me than you, and thank you from the bottom of my heart.
Okay, we're now going to fast forward a decade to the 90s, and it's my pleasure to introduce James Gortzman. And I'm going to try to tell a little story for everybody. And my favorite story about James is that, okay, when he was an undergrad, based on the work he did as a thesis, we got invited to submit a paper to a conference. And I read this paper again maybe 5 or 10 years ago. And in it, in 1995, James essentially outlined what would become Web 2.0 in an amazingly clear vision. So given that track record, I'm really looking forward to what he's going to tell us about the early glimpse at the post-cloud era, because I think we should all just go start doing our startups immediately. So, James.
Yes, OK. So there's actually a really fun symmetry to being here today, because the first time I ever presented to a group this large was as an undergraduate here at Harvard, and it was because of Harry that I was doing it. Back then, Harry, I was a CS major, and Harry was my academic advisor. And he had asked me to join this thing called the Faculty of Arts and Sciences Information Technology Committee. I don't remember this. And so I was the student representative. My first time being on a committee, very educational experience, has served me well in my career. And back then, this is an organization committed to sort of bringing information technology to the entire Faculty of Arts and Sciences community. And the topic of the day was bringing high-speed Ethernet to every dorm room. Because it's hard to imagine, this is just 25 years ago, but it was sort of this, the web has happened since then. Just to have some context, when I came in as a freshman in 91, 20% of the graduating seniors had email addresses. When I graduated in 95, 100% had email addresses. When I came in as a freshman, there was no web. When I graduated as a senior, there was a web. The mosaic had happened. And so this is really, I feel very lucky, actually. I was a student at this sort of, epochal time in sort of information technology. And anyway, he had asked me to be in this committee, and the committee's job was to get all these dorms wired. And so I use this talk as a chance to go back and do some sort of information archaeology. So I'll share with you some fun things. One of the things that I put together was an Adopt a Dorm program. So these are students helping fellow students get their computers plugged into this newfangled internet. Because back then, you didn't just plug it in. You had to install cards and special drivers, and it never worked. And so it was a major pain in the ass. Anyway, this is a questionnaire we put together, and we sent around in April of 93. And I want to share a couple things here. Do you have an email account, yes or no? How often do you check it? And the most frequent option here is every day, right? That is the most frequent opportunity for checking email. Every month, I don't use it, or other options. What do you use the internet for? Anonymous FTP, WASE, W-A-S. I had to go back and go, what was WASE? I didn't remember. Gopher, who remembers Gopher? Gopher? There you go, okay, Gopher. Telnetting to a BBS, Usenet News, a computer class, other. Again, no web. This really dates where we were at that time. So put this in your head back in 93 now. That's the state of where we were. And so I remember putting together this bulletin for the fellow students who had signed up to be on this group ushering Harvard into the next generation. And Margaret's talking about my prophecy. Well, there you go. The class of 97 graduates. This time before the network was a very primitive time indeed. This is back in 93. In fact, I don't know if Expos was in fact the first thing to actually use the internet, but that was something we predicted. This is also fun. This is an article from the Crimson talking about this organization we put together, training students to go into the dorms and help other students wire up. This is actually fun, because this is actually a memo. You probably can't read this. I'll read it to you. This is a memo of the office hours we assigned, because we started the freshmen were the lucky ones. They got the high-speed internet before everyone else did, because we started the freshman dorms. So all of us upperclassmen who actually needed the internet for things like our classes had to keep trekking to the Science Center, while these freshmen got to probably the first ones out there looking at cat photos or something in their dorms. But I went through, these are all the students who were, get to each of these are all the freshman dorms, and we had students assigned to come in and help them wire up the Ethernet. And so I actually went into LinkedIn. What's that? Yeah, so Craig is on there, right? So I actually went in and did a Where Are They Now comparison. So I went to LinkedIn, and so these are the roles I was able to dig up for that initial group of students. And so yeah, we have first employee Google, right? So that was Craig Silverstein, now Khan Academy. We have CIOs, we have CTOs, we have CEOs. So I don't know which came first, being on that early group of internet science or being a Harvard student. But that's a Where Are They Now slide. And then finally, this is the other thing I'm kind of proud of. You talk about the prophecy thing. I think we claimed the mantle, the first group to ever actually create Facebook. Because back in '94, I gave this talk to, the talk that I was alluding to was addressed to alumni. And I was speaking on behalf of this IT committee. And I was a young Turk. I was a young student here to talk about all the wonders of this brave new internet we just spent all this money, I think it was like $1 million or something, wiring the dorms with Ethernet, and why this was a good thing to have done. And I talked about some of the things we accomplished. And one of the things I mentioned was we had just put the Facebook online for the CS department. And CS students could now go to this thing called the web, and they could look up each other and see pictures, and students could customize their pages. And I mentioned my friend John, who's actually here, Jonathan, he had mentioned he was going to put his mom's banana bread recipe on his page along with Harvard Frisbee schedule, which is ironic because Jonathan has a Facebook page today, and it's all about food. And so I think it's nice to see that some things actually really haven't changed. You know, the more things change, the more we come say the same. So in terms of now to kind of bring it back a little more current, Margot had asked me specifically, how did my time at Harvard help me prepare for sort of my career? And I kind of thought about that, and it's funny because there's a very direct, straight line from my current career back to Harvard, because I am now CEO and founder of a company building technology for computer games. And Margot had asked me back, so I did a thesis, and it had nothing to do with computer games. But as my thesis advisor, I got to know Margot very well. Back in 2009, she had asked me to come and speak at this thing called the High Performance Transaction Systems Conference on how games were now, in fact, high performance transaction systems. And so you have this, I love it because you have this is actually how I feel today. Here I'm at Harvard, I'm talking as a commercial guy, not the academic. Here's all these great talks on things like, you know, enterprise cloud storage services and all these things. And here I am talking about playtime's over. Right now, my talk was like games and why games are actually cool. And so this talk led me to come back in 2013, another talk at HPTS. And at that point, I was talking about how the academics have let us down. That we in the game industry were really struggling at that point to keep up with our own success. Because this is a game called The Simpsons Tapped Out. Back in 2013, I was working for Electronic Arts. They just bought this kind of PopCap I was at. And we launched this game. And this is one of the kind of big all-time fails of EA, because this is what had happened. They launched this game back in April of 2012. And it hit #1 on the App Store like right away. Boom, instant #1 hit. And within 4 hours, it had completely collapsed. The servers had collapsed. It couldn't keep up with the load. They had to take it down for 4 months, rebuild all the servers, relaunch it again in August of 2012, and then went right back to #1 and stayed there for like 2 more years. But the fact that, I mean, most companies, EA survived that 4-month outage. Most startups would not have survived. And so the question was, what had happened? And the answer is, gamers are really shitty at building powerful distributed systems. This is a hard problem. And I was sort of, at this talk, railing against the tech community, saying, you've let us down. Your databases don't work right. You can't just throw massive load at these things and have it just work. You know, and so the irony is I gave this talk, and that kind of sparked an idea. And in fact, that led to the company I now run called PlayFab, which does exactly that for the game industry, which is provide services at scale for game companies. And so we've built this company that provides all these different services game companies can just use and consume and not have to worry about scaling, because we've kind of done that for them. And the reason I'm talking about this, I'm not just in the great Harvard tradition of humble bragging. I mean, the reason I talk about this is because we're a small company. We're only 14 people. And yet, we're able to run a business that is actually at a pretty massive scale now, all because of this thing called the cloud. So part of what I'm going to talk about today is how the cloud is doing amazing things. Because I think people hear about the cloud all the time. And unless you're actually out in industry, you don't quite appreciate just how incredibly transformative this has been for us. So this gives you a sense. This is actually going back now about a year and a half, tracking how many players are playing games that my company now powers. And so we're up now to about 6 million daily active players. We're running at about 50 million monthly active players. And if you look at the number of API calls that turns into, we just recently hit a peak of about 500 million API calls per day being run off of our servers. That's a lot of load. That's something like 10 or 12,000 transactions per second. So just in the 10 minutes I've already been up here, some ridiculously large number of API calls are happening out in the cloud somewhere 24/7. And what's fun about this is we're a 14-person company. We can't afford to have one of these. We don't have a massive operations center. I mean, we all go home and sleep at night, right? So how do we do that? How do we run a service that runs 24/7 with millions and millions of players around the world in every time zone that doesn't go down? And the answer is the cloud. And the answer is, there's some really neat things have happened that allow small companies like ours to have that kind of scale. So what are some of those things? So I'm going to talk about a couple of them. One of them is this software as a service, SaaS. You may have heard of it. It's amazing what that has meant for small companies like ours. In particular, we now can stand on the shoulders of giants. Because the real transformation, in my mind, of the cloud is that companies can now plug together like Lego blocks all these other services from all these companies in a pretty seamless way. So for example, we ourselves live on Amazon Web Services. That gives us things like compute and storage and data pipelining, these kind of basic building blocks. But we also rely on things like Snowflake, which is a massive data warehouse in the cloud that we can just subscribe to and use and not have to manage. Pingdom is a service that does nothing but ping your servers every 30 seconds to make sure they're running. And if they don't run, they tell you. But it says someone else's data center, which means that when we go down, this is how we know about it. And it's a real thing, and it's very useful. Datadog is a massive service that collects all of our metrics. So we send Datadog 70,000 different numbers on a continual basis, and they give us pretty graphs and let us know how things are performing. Zendesk is our ticketing system. Loggly does nothing but scoop up all the server logs from all of our servers and put them all in a massive Elasticsearch-powered system where we can go in and search them. So if something goes wrong, we can go back and conduct kind of forensics to see what happened off of Loggly and not have to manage our server logs ourselves. Status page does nothing but run our status page. So if you go to playfair.com/health, there's a green list of servers that are up. And this really helps us because recently Amazon S3 went down for a couple days and it was a big deal. They didn't go down. So we were able to have a little red light saying one of our services was impacted, and people could go and find out what was impacted. And that didn't go down because it's a whole different data center. Stripe is our payment system. VictorOps is my favorite. VictorOps does nothing but essentially paging services in the modern day and age. So if Datadog does all of our monitoring, if Datadog detects a problem, and it's a problem big enough that it needs to wake someone up, it then automatically tells VictorOps, hey, there's a problem. And VictorOps has a whole call list. Our engineers take turns being on call. And there's a whole call list rotation. And it's all set up in VictorOps. And it'll automatically start calling and paging and texting. And after 10 minutes, the first person doesn't answer. It'll fall over to the next person, until someone eventually wakes up, goes online, turns off the alarm, and solves the problem. And that's how a 14-person company can run a 24/7 service. And the thing is, it actually kind of works. We depend on all these other tools we depend on. So GitHub is our source control, right? I mean, the nice thing about PlayFab is we're 14 people. You could burn down our entire office today and zero would change our business. There's not a single thing stored in our physical office that matters. Everything's in the cloud. All of our source code, everything. We don't, we're a completely virtual company. We have an office just for convenience. It's nice to have a place to get coffee and chat with your coworkers, but we don't have to. Slack, frankly, is our new virtual office. Slack is a system of, and everyone here using Slack users, you all should be on Slack. Slack is basically it's like a BBS, but like modern BBS. It's a thing we use to communicate with our colleagues and post files. It's also how we do all of our customer support now has moved to Slack. It's how we communicate with our customers and keep up with what they're doing. Trello is our board for tracking tasks. Jenkins is our continuous build and automation system. So when you check in a build, anytime anyone checks in anything to GitHub, it automatically fires off a job in Jenkins to run through a few thousand tests, make sure everything passes the automated testing. Once it passes, Jenkins is how we then roll out and deploy. It's all automated, the deployment process. Fabricator is our system for code integration. I can go on and on. But the point is, these are all building blocks that a company like ours can roll along and just wire them all together and start using them. And that, to me, is really the transformative power of the cloud. This, for example, is a screenshot from Datadog, just a little glimpse of probably 20 of the literally hundreds of different metrics and graphs we track to measure the business. Every one of those has automated alarms behind it, which is how we know when things go wrong. This is actually Slack now. This is showing inside Slack what happens when something goes wrong. So I went back in time. You can see at the top there, triggered PlayStream processor high latency on shard. That means basically the latency started growing on one of our key metrics. So something's wrong. If the latency is growing like that, it's a bad thing. So you can see VictorOps now chimes in, notify, trying to contact OREES for 2 incidents, sending SMS. He then acknowledged it. So once he acknowledged it, it then canceled the paging. And then Matt, one of my CTO, jumps in and says, hey, I'm looking at this now. He then fixed it. VictorOps is resolved. You can see the Datadog alarm went down. Everything's solved. And this whole thing took from 8:50 to 9:55, about an hour total but basically was solved in about 20 minutes. So that's an example in real time of what happens under the covers when you don't have a dedicated 24/7 network operations center, but just a bunch of engineers working on the laptops, wherever they happen to be. This is a screenshot of our continuous integration, just to give you a sense. Every time, this gives you a sense of all different automated tests we run on a regular basis every time code gets checked in. This is actually the thing that's probably had the biggest impact on my business. So PlayFab, 14 people, we've had 10 minutes of downtime in 3 years of operation, right? That's like 5 nines or some crazy number of nines. And part of the way we do that is the cloud. So it used to be in the bad old days, you had dedicated hardware. You had to actually physically buy servers and rack them in data centers. And that was a major capital expense. So we never would have been able to afford 2x the number of servers. We would have had probably 1.2x or something the number of servers. And so what it would have meant was you're running a given build. It's time to roll out your next build. You do what a lot of people do. They say, we're down at midnight. From midnight to 2 a.m., we're offline. So you take it all down. You switch to a new build, and you spin it back up again. That's how you used to do it. Now, we simply spin up an entire complete duplicate of everything. So we have PlayFab running with all this stuff. We push one button. It basically spins up a complete copy of everything. Duplicate servers, duplicate databases, everything that's duplicated. You then start running, and then we have this big DNS switch. We basically switch 1% of the traffic over. And then we start running on that. And then if there's no problems, after a couple of minutes, we then switch 10% over. And if that works OK, we then switch 100% over. And once all the traffic is running on this duplicate version, we just shut down the old one. And it all just kind of goes back into the cloud from whence it came. And we're now running on the new build. And that's how we switch over traffic. And that's great, because it means no scheduled maintenance windows, no scheduled downtime. Where it really becomes impactful is when you've got a problem. Because in the old days, you'd switch everything over. You'd start ramping up your new build. Oops, you got to roll back. And then you got to do it all again just to roll back, if you can. And a lot of times you can't even roll back because now your databases are completely screwed, and now you're just stuck. In the new system, we switch over. Oops, problem. We just switch it off. Maybe no one even noticed if we're lucky. And that's the real power of what the cloud has meant for how we can run these massive systems. OK, so I promised a little glimpse into kind of what I think is where we're going. So that's the cloud. And the cloud is so powerful because Amazon and Google and Azure now is providing all these resources. You can just go online, and with a credit card, you can basically get, I love it, they call it compute. You can get compute. Compute is servers, EC2 instances. You can get storage, databases. You can get all these services. Where it's going, though, is actually, it's interesting. One of our largest customers, this is the journey that one of our largest customers has gone down. So there's a huge game company. I'm not going to name them, but they've got lots and lots of players and lots of games. They've been around for a long time. They used to run their own data center. And as you did. And then they realized, well, that's too expensive and too time-consuming and too much resources. So they went to Amazon, as a lot of people did. And Amazon was great. And it saved them a lot of money. They could lay off a lot of people, and they could cut their costs or reallocate to other things. And that was great. But then they realized that was too expensive, because they're still doing basically the same thing they did before. Just they didn't have to physically rack servers anymore. But they were still having to spin up servers and manage storage, and things could still go wrong. You could still end up with running out of compute power or whatever. So then they went to Google Cloud. And Google Cloud was great, because the way Google Cloud is different from Amazon is you don't need to worry about the physical servers anymore. You literally just give it the code, and it will just sort of magically give you enough compute power to run your stuff, as I understand it, sort of my layman's version. So that was great, because it meant they could let fewer people go. Fewer people needed now to run their services. But they still were running code. They still had to write the code. And this is a large company that has a massive, very powerful info security group, such that every single line of code that's written is seen as potentially company-ending code, because any code out in the cloud, any code written on the server side could introduce hackers and viruses and things. So it had these massive security processes. So that was still too expensive. So now what do they do? We're doing it all for them. And literally, they write zero code now, because PlayFab is this magic set of services that does everything for them. And so basically what they've done is they've gone from having to build and architect their own back-end services. And that's my poor job of trying to diagram what that looks like. But they went from having to build and write their own code in the back end, which was expensive, to just, we have like 300 different APIs. And they just use our APIs. And it's a vertical set of APIs. So we've got APIs for things like update user data, add friend, get user inventory, add user virtual currency. I mean, these are pretty not sexy APIs, but they're very tied to what games do. So we've got this nice set of 300 different vertical APIs for games, and they just use them. And that's it. It just works. And when I look at what's going on in things like Google Firebase, same thing. Google Firebase is similar. It's a set of services for any mobile app. And the goal now is to no longer need servers at all. You just consume, I mean, you're still using servers, but not your servers. You're just consuming services from these APIs that are increasingly tuned to your particular need. So we do this for games. Firebase does this for sort of broader mobile apps. I'm sure there will be others. And so my prediction, such as it's worth, is that we will soon be in a world where more and more this will crop up, servicing these various verticals, and you will no longer need to worry about your servers at all. You just will build your apps, all client-side, and all the magic that happens out there is all done with APIs, and that's sort of the world we're heading towards. So anyway, hopefully that sort of was a fun tour of sort of what I'm up to, where we've been, how Harvard has kind of got me to this point, and I owe my start to some of the early committees and thesis advisory from Harry. So with that, I think we have a little bit of time for questions, a little bit, about any of this stuff or none of it. Yes? OK, great. Happy to chat more. Oh, over there, yeah. Distributed risk, like catastrophic failures?
You have 14 suppliers distributed all over the internet. When they go down, what happens to you and how do you manage?
Yeah, huge problem, and you're exactly right. So we've gone from sort of managing all of our risk ourselves to now having all these other people kind of distributed the risk out. On the other hand, I think a couple thoughts there. One is, so Amazon is obviously our biggest supplier, and they are able to address risk in a way that we never could. So for example, we run in what's called 3 different availability zones. Availability zones are completely different data centers, different power supplies. As a small company before, we would have had probably 1 data center with 1 power supply. Now we have 3. And so right away, we are already getting benefits of scale. We've had situations where one's gone down and we've been OK. Also, things like denial of service attacks. We never could have afforded to defend ourselves against concerted denial of service attacks. Amazon has all these layers in place to prevent against that. So I trust them way more than I ever would have trusted myself to sort of defend against those things. The fact that we've got all these suppliers now doing different things, I actually think it's built in a certain amount of fault tolerance, because no one of those, let's go to Amazon, no one of those is necessarily mission critical, right? A piece can go down and we degrade our service a little bit, but it's not out completely. If Loggly goes down, we lose our log files for a while, but the service still runs. If Amazon goes down, we're kind of screwed, but that's really the only point of failure. So I guess the compounding of the different services I actually see is now a strength versus a weakness, and especially because they themselves are often running on different dependencies. All we need to do now is add Azure or Google, and we'll have actually pretty good backup even for Amazon at this point. So anyway. Yep, thank you.
OK, so now we're going to go back in time. We're going to go to the mid-'70s. It's my pleasure to introduce Guy Steele. And my little nugget about Guy is that Guy keeps things. Guy keeps a lot of things. We have a room at Oracle we call the Guyberry. So when I mentioned the existence of this event, Guy, who took the very first course Harry ever taught, walked into the Guyberry and showed me his notebook from the very first course Harry ever taught. So on that note, Guy, take it away.
All right. OK, so I want to talk to you today about the most popular programming language in computer science. It's a very interesting language, widely used, but has no interpreter or compiler. Doesn't seem to have a specification written down everywhere. We're not quite sure who invented it, though these people designed some key features. And yet there are other features of the language whose history is actually rather difficult to trace. And I would tell you the name of the language, but it doesn't seem to have one, despite being the most popular programming language in computer science. So for the purpose of this talk, old habits die hard, I'm going to call it computer science meta notation. And in this language, you've got user-declared data types that are usually written out in the form of BNF, in Backus-Naur form. Its code is written in the form of inference rules, the so-called Gentzen notation. We'll see examples of that in a minute. It has this very interesting, weird symbolic operation called capture-free substitution, for which we can thank Alonzo Church. And more recently, it has developed features for expressing repetition through means other than recursion. So overlines and ellipsis notation are going to be particular objects of study. And it's a very beautiful language, and unfortunately, in the last 10 to 15 years, it's getting badly messed up And we may be approaching a crisis. I think we need to do something about it. So here's an example of computer science meta-notation code. It's in the form of a Gensen inference rule. There's a conclusion below the line and some premises above the line. And the essence of it is that if you want to prove the thing below the line, all you need to do is prove the things above the line. And I've highlighted some things here to draw your attention to the fact that some things have been overlined. And the intent of those overlines is to indicate repetition of the thing before it. We're going to talk more about the precise nature of that repetition later on. Here's a different piece of code. This is taken from last year's POPL conference in 2016. This is a collection of 7 rules out of a much larger collection of about 30 or so rules. This is a type checker. And this shows how, given a context gamma, you can figure out what the type of an expression x is, and say that its type is ta. And for each of the different possible kinds of expressions, we have a rule here. Now, I'm not going to dive into the details of this, but I'm going to point out that you can view each of these rules as being a kind of subroutine. The way to see that is to realize that you can regard the gamma and the expression to be looked at as inputs, and you want to get a type out. And given an expression, all you need to do is find the rule that matches that expression and then apply it. And this choice of rule is the main source of conditionals in the language, non-deterministic dispatch to rule. Now, this particular program happens to be deterministic because the rules have been carefully written so that for any given form of expression, exactly one rule will match, or at most one rule will match. If none matches, then you've reached a situation where you aren't able to do the proof. But you can view each one as a subroutine where if you want to view what is below the line as a function signature, as sort of the entry point, then what is above it is the things you need to prove in order to prove the thing below the line. Therefore, that is the body of the subroutine. It's the things you have to execute in order to achieve the effect of the subroutine call. And here in the same code, I have highlighted 2 uses of ... the ellipsis, to indicate a sequence of things. And it's being used in 2 different ways here. In the premise, highlighted in yellow, it is being used as an iterator. And its intent is actually that the premise before it occurs a bunch of times, once for each value of I. Whereas in the conclusion below, it's being used to indicate a sequence in a single expressions, that you have a bunch of m's that are being fed as an argument to this operator. And that's about all there is to say about that. But notice the use of ellipses to indicate some form of repetition in the language. OK, so I hope that I've convinced you that it's a programming language. In fact, the code I just showed you is part of a complete type-checking algorithm. Now I want to show you that it's the most popular language in computer science, not in the use not in computer applications, but in computer science. Here I did a study of the last 43 years of POPL, which is ever since its beginnings in 1973. This is the Principles of Programming Languages conference. And the total height of each bar is the number of papers in that conference. These are actually aggregated into 5-year intervals. And the light part of the bar at the bottom is the fraction of papers that are using inference rules as a part of their notation. And as you can see, the fraction of such papers has been growing. And for about the last 20 years, over half of all papers appearing in Principles of Programming Language conference have used this notation as part of their presentation, often as a central part of their presentation. But what about other conferences? Well, I looked at the last 3 years of PLDI, of OOPSLA, of ICFP, the International Conference on Functional Programming, and PPOP as a control. That's the Principles and Practice of Parallel Programming. And you can see about 1/3 of PLDI papers in the last 3 years are using this notation, about 1/3 of OOPSLA papers, roughly 2/3 of functional programming papers, and almost none of the papers in the conference on parallel processing, because the parallel processing conference tends to focus more on what's going on at runtime than what's going on at compile time. Computer science metanotation tends to be used to describe compilers and their associated algorithms. Nevertheless, it's a very widely used notation. So in order to produce these results, I had to eyeball these papers manually, or I should say ocularly, because unfortunately the essence of this notation is that horizontal line that indicates the Gensen notation. That's not captured by OCR. And so it was necessary to actually physically get the paper proceedings out of the library. I've got copies of them all, of course, and flip them over, looking at it page by page. Oh, there's some Gensen notation. I take notes. So I've studied about 25,000 pages of computer science papers in order to distill these results. Okay, now I'd like to talk about some aspects of this notation. The first is the use of Backus and Hour form. Here is the Backus and Hour form as originally designed by Backus. This is used in his initial report on the International Algebraic Language. in 1959. And you can see that this is typed with a typewriter and then has a bunch of things drawn in by hand, with overlines over the word or. And the equivalent sign is actually an equal sign with an extra line drawn in below by hand, that kind of stuff going on. The angle brackets are drawn in by hand. So this is a very labor-intensive notation in the day. When this report was revised the next year, Peter Nauer was the editor. It was published in CACM. And the notation had changed a bit, partly to make it much easier to keyboard, and partly Nauer instituted the convention that the non-terminals of the grammar should be English phrases that correspond with English phrases used in the text describing the language, so you could easily see the correspondence. And it's for those contributions that Knuth wrote a letter indicating that it ought to be called not Backus normal form, but Backus Nauer form. But since then, the various other versions of BNF have occurred. I've unearthed 20 or 30 different variations. I'll just show you 3 or 4. This is a notation that's used to describe the Bliss programming language in 1970. Instead of the colon equals, there's a little right arrow there. And what's interesting is that in this document, the notation was just taken for granted, even though it was a variant. They just said, here's the grammar. Did not describe the notation used to write the grammar. In 1977, Niklas Wirth noticed that there were a bunch of different variations of BNF, and he thought this was causing confusion, so he decided to solve the problem by presenting yet another variant. And it's actually a pretty nice one, and 20 years later it became an international standard, which is now widely ignored. In part because the next year, Karen Henry-Ritchie published their book on the C programming language and used yet a different version of notation, which is obviously BNF. But here, instead of having vertical bars to separate the choices, they just put them on separate lines. The colon equals is shrunk to a single colon. And there are 2 different versions depending on whether the alternatives are single symbols or phrases. And this has been widely used to describe C, C++, Java, C#, F#, and other languages. Okay, so we've seen a bunch of different varieties of BNF over the last 6 decades. And this largely hasn't been a problem. People seem to accommodate to it. And I think that's because the elements of the structure of the notation always appear in the same order, whatever the variant. The punctuation changes, but roughly the notation stays the same. And so when a student or a veteran of 40, 45 years like me walks up to paper and sees, oh, that looks roughly like BNF, I think I can figure it out. That's fine. And in fact, the version we use in computer science papers is very different from any of those. Here's an example taken from a 2014 Pubble paper. Here's some BNF, and it's obviously BNF has got the colon equals, it's got the vertical bar, but instead of using English phrases from the non-terminals, we've got single letters here instead, often Greek letters. And so the mnemonic value of the non-terminals has gone away. And so suddenly comments appear. So instead of having uncommented BNF that was self-describing, now we've got this very compressed BNF for which we need comments so we can tell what's going on. Okay, so why have we gone to single letters? Also notice in this BNF the use of the overline to indicate repetition, whereas in original BNF one would have used recursion. In the last few lines of this BNF you'll see overlines to indicate that elements are repeated. Well, I believe that there is an obvious evolutionary pressure to make BNF more and more concise, and in fact to make CSM more and more concise, which explains a lot of its structures. And that evolutionary pressure is conference page limits. And as the algorithms become more and more complicated and the page limits don't change, we are driven to make the notation ever more and more concise. I think this is real, and this is something we need to worry about. This is something that has been sort of implicit all along, but I'm a language designer, and I want to think about what are the consequences of this for the future design of this language as it evolves. And there are implications. Okay. Another couple of interesting aspects about BNF that I have not seen remarked upon before, and so this is my own contribution. I think it's the source of my own analysis, which is there are a couple of conventions about how we use BNF. If we took the definition of BNF literally and used it everywhere, it says that wherever you see a non-terminal, you can replace it with an expansion described by the right-hand side of the rule for that non-terminal. So if we took that definition literally, then we could replace every non-terminal by a string derived from that non-terminal. And if we were to write an English sentence such as, a value of type ta may be assigned to any variable of type ta. Well, ta is a BNF non-terminal. It expands to a data type. It can expand int. It can expand to bool. So let's expand the first instance to int and the second to bool. Now we have a value of type int may be assigned to any variable of type bool, which is not what we want. It's nonsense. Instead, we had this implicit convention about consistent substitution when a non-terminal appears anywhere but on the right-hand side of a BNF rule, if it appears in an English sentence or paragraph, or if it appears in an inference rule. This is very important. Then we depend upon consistent substitution. If the non-terminal is mentioned more than once, the same expansion must be used for each occurrence. So we get a sentence of the form, a value of type int may be assigned to any variable of type int. There's a second related rule. If we took the definition of BNF literally and replaced every non-terminal by a string derived from that non-terminal, even if we obey the consistent substitution rule, then we have a sentence such as, if ta1 equals ta2, then ta1 is a subtype of ta2. That would be expanded with, say, ta equaling int 2. If int sub 1 equals int sub 2, then int sub 1 is a subtype of int sub 2. But that's not usually what we want to say. Instead, we have this implicit convention that when you decorate a non-terminal, and what I mean by decoration is things like subscripts or primes or accent marks, or possibly little subscripted names. We recognize such a decorated non-terminal as in effect being a distinct non-terminal that has the same productions as the undecorated form. And this allows us to produce such sentences from your thing up at the top as, if int equals bool, then int is a subtype of bool. Now, in fact, that is a true sentence because int is not equal to bool. We've consistently substituted for ta1 and for ta2. And we also get the sentence, if int equals int, then int is a subtype of int. Yay. The point of all of this is that we have implicit conventions about this programming language that have not been carefully written down up to now. And they have to do with being very careful about what things must be the same and what things are allowed to be different. And what more important distinction could there be when you're worrying about your mathematical notation and your computer science notation is being very careful about when things must be the same and when they need not be. So now let's talk about substitution. The substitution notation this substitution notation was introduced by Alonzo Church in 1932 when he was worrying about formulas and substituting for variables and formulas. In 1941, he published the Calculi of Lambda conversion. And here there's a crucial difference. In 1932, he simply spoke of substituting an expression for a variable everywhere it appears in another expression. That's all he says. But in 1941, he says, to replace any part of a formula by this substitution, provided that the bound variables of m are distinct both from x and from the free variables of n. So at this point, this becomes capture-free substitution, which has been a very important idea in computer science. Okay, and so of course now we use this notation to this day, not. Nowadays, we tend to write something like this. I'm not quite sure where this notation came from. I've been trying to trace its roots. We write something like the expression produced by substituting the value v, or the value expression v, for the variable x within the expression e. And we write something like that. So, but other variations are seen in computer science. Any guesses as to how many different variations of this notation are in the literature? 43. All right, do I hear any other bids? Okay. Okay. Well, for Popple, from 1973 to 2016, I documented 28 different varieties. And they're shown here in this table. And the usage has grown over time. Substitution is, in the last 5 years, has been used in over 1/3 of Popple papers. The inference rule is in over half, but substitution in over 1/3. And we see all these different variations. You say, oh, well, it keeps changing over the years. But in fact, the number of variations has grown over the years. If we look at other computer science conferences as well, then I've been able to document 31 variations, of which 15 were used at Popple in the last 5 years and 5 more at other SIGPlan conferences in the last 3 years. So that tells us out of these 31 variations, 20 are now in live use. Why are there so many variations? I haven't quite been able to figure that out. So, well, we had variations of BNF, and that hasn't been a problem for the last 6 decades. But I think it is a problem for substitution because these variations don't just change the punctuation, they change the structure. They change where the V and the X and the E are. And so when you walk up the notation, you can't easily guess which piece is supposed to be which. And so we have a couple of problems. One is a moderate problem. By far, the most popular form is E with a postfix set of brackets and V before X and the slash. But once every 5 years, we see this other version that gets it backwards. It has the X before the V. And you can't count on the variable names to tip it off because different authors use different variable names. I even found one paper published last year that used both forms with no comment or explanation. I assume that one of them was a typo, and I can't tell which one. Okay, so that's a moderate problem. The more difficult problem is that some of these forms, particularly the ones using the maps to arrow and the colon equals, and also the variants that are prefixed rather than postfixed and use braces instead of brackets, those forms are fairly frequently used. They're used in about 1/6 of all POPL papers. So these forms are fairly common, but they are also widely used for a completely different purpose, for function update, also known as map update or heap update or storage update, standing for this notation down here at the bottom. A function f updated so that x maps to v, when applied to z, is if z is x, then return v, otherwise return f of z. So it changes f, so at just one point in its domain, it has a different value in its range. And that kind of feels like substitution. There's this vague idea of, yeah, we're changing one thing to be another thing. We're substituting this value for this particular variable. This is actually a very different operation. Substitution has this whole extra piece of machinery where it goes groveling through an expression and dealing with avoiding the captures, the variable captures. And none of that is a part of the function update thing. So if you see a paper and you just see this notation in the middle of it, you're unsure whether it's function update or substitution. And often both kinds of notation are used in a single paper. And lately, most authors, under the pressure of conference page limits, are not taking the space for that paragraph that explains their notation. They're just taking their version of the notation for granted. And it's become very hard to review papers. In fact, I started this entire investigation in metanotation because I noticed in reviewing papers for ACM the last 4 or 5 years, I'm having more and more trouble reading the notation because the authors aren't telling me which variation they're using. So much for substitution. I think we've got a problem with substitution. Now let's talk about overlines. Here's a history of the overline notation, all compressed into one slide. Believe me, I could spend 2 hours just telling you about the history of the overline. But let's go through this. In 1484, Chiquet used an underline to group symbols to be a single mathematical expression. In 1525, Rudolph used dots. So that dot means that the initial square root symbol is a little more separated from the rest of it. As a result, the addition happens before that initial square root. In 1556, Tartaglia started using parentheses for mathematical grouping, very different notation. In 1631, Ottred used a double dot to indicate grouping in the same way that Rudolph used single dots. Why did Ottred use a double dot? Because he wanted to use single dot for something else. Okay. In 1637, René Descartes attached an overline as a grouping symbol to the surd indicating square roots, producing our modern square root symbol. And this is where the overline as a grouping survives most widely in our current mathematical notation. In 1640, Jan Stampoen used all three together. He added together 3 terms, and then he put them in parentheses, and then he drew an overline, and then he put a dot just to make sure. He was taking no chances, so whatever notation his reader was familiar with, they had a fighting chance of understanding what he meant. 6 years later, van Schoten, editing the works of Vieta, decided to use overline for grouping of mathematical expressions. Leibniz also used overline early in his career, but in 1702 he shifted to using parentheses, and the reason was technological. He said the parentheses are much easier for the typesetter, setting type by hand, than to deal with in overlines. And so he recommended a changeover from the overlines to parentheses, and in fact, 6 years later, Acta Eruditorum, I love the title of that journal, Acta Eruditorum, the Acts of the Erudite, officially adopted the Leibnizian symbolism and switched over to using parentheses. And a little later in that century, Euler and 2 of the Bernoullis widely popularized the use of parentheses, and I think it's due to their writings that we now use parentheses so widely today. But a century later, Giuseppe Peano, as in piano arithmetic, decided to use dots instead. And so he reintroduced the use of dots, and he used both single and double dots and occasionally triple dots. And you can think of the number of dots as corresponding to binding weakness. So A:(BC dot D means, well, B and C have no dots between them, so they bind first. And then that product binds to D because there's a single dot there, and then to A because of the double dot. And that might have died, except that Russell and Whitehead decided to use Peano's dots, thereby keeping the notation alive and making their work much harder to read a century later in a parenthesis world than it would have been otherwise. So here we see that for 5 centuries, there have actually been 3 competing notations for grouping of mathematical expressions, duking it out. And except for Principia Mathematica, it kind of looks like parentheses have won, except that now we're seeing the overline come into wide use in computer science, not only to indicate grouping, but also repetition. And so how did that happen? Well, first I need to make a digression into the history of vectors. Okay, so in 1813, Argand, of the Argand diagram, graphs complex numbers, speaks of the square root of -1 as describing a rotation of the plane, and proposes the arrow notation for vectors. Notice that this over arrow actually kind of groups the symbols A and B together, indicating the start and the end point of the vector. 20 years later, Hamilton recast the theory of complex numbers as a pure algebra on pairs of reals. He didn't want to think about imaginaries, he was just thinking about an algebraic structure. And so he really liked this algebra on reals and decided to try to find corresponding algebras for tuples of length 3 and greater. And he particularly focused on triplets. And after 10 difficult years, finally discovered the quaternions, which are actually 4 tuples. And so they're like complex numbers with I, J, and K. And the I, J, and K correspond to the triplets he was looking for, but he discovered that he sort of needed this extra thing in there. What was that about? So a few years later, he managed to reformulate quaternions without using explicit coordinates, describing the quaternion as the sum of a scalar and an imaginary vector. And a few decades after that, James Maxwell used quaternions to describe electricity and magnetism. His first works were written using quaternions. And he made some mild criticism about how awkward the quaternions were to use. And not long after that, Gibbs established dot and cross for our dot and cross product symbols. They haven't been around forever. They're fairly recent as mathematics goes. And then in 1882, Oliver Heaviside, the physicist, advocated ditching the scalar part of quaternions and simply using vectors. And here's why. Quaternions are kind of awkward to use, in part because the vector is imaginary. So when you try to find the length of a vector, you take the dot product with itself, but because it's imaginary, the length comes out negative. So you end up having to put in a minus sign. And when you're working with quaternions, you find these minus signs constantly popping up in places that are physically unintuitive. So Heaviside says, forget the scalar part of quaternions. Yeah, it's algebraically pretty, but let's just use the vector part and not worry about the signs nearly as much. And there's a big fight in the 1890s between the quaternionists and the vectorists and physicists in physics. The quaternionists pointed to the beautiful complete algebra. I mean, quaternions are a field. But unfortunately, they only describe the three-dimensional case. Right? They're great for describing rotations in 3 space. They're still used in video games to this day for that purpose. But vectors have a much cruder and clumsier algebra. The multiplication is badly behaved. In fact, dot and cross products are not true products. They're just these weird binary operations on vectors. But they have the virtue of being very convenient, and they have the virtue of generalizing to more than 3 dimensions. And they eventually won out. And we can be thankful. This is where they entered into computer science. My physicist friends cringe, but in 1975 to 81, we see both A with an overline and A with a little arrow over it used to denote a vector, by which a computer scientist doesn't mean this thing that transforms in certain ways in physical space. They just mean a list of components, in other words, a one-dimensional array. So it's kind of a bastardization of the concept. But the word vector or list or sequence or set are all used to describe this idea of a sequence of things A sub 1 through A sub m. And by 81, that notation is taken for granted, at least in Popple papers. And by 89, the enclosures, the angle brackets, the parentheses, the braces are no longer required. It's the notation X with an arrow over it is described as indicating an unenclosed sequence of things, but comma separated. So far, the semantic model being used by the computer science appears to be that overline marks a variable as representing a sequence. But there's a corresponding syntactic model, which is that you just make copies of the overline name and spread them out from left to right and attach sequential subscripts starting from 1. And that is its meaning in a paper. The next year, we see an explicit claim that, in fact, the thing that is overlined may be a metasyntactic variable, that is a non-terminal of the BNF. And also in that same year, we see this stretching in the notation for what I call an implicit unit replication. A paper writes M with an overbar, and then a colon, and then sigma with an overbar, where M is a variable name and sigma is a type, and uses it to mean M1 colon sigma 1 dot 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 MK colon sigma K, rather than to mean a bunch of M's, then a single colon, and then a bunch of sigmas. So in other words, the overline has kind of been distributed in this weird way in the writing, but the intent is that a single larger syntactic unit get replicated. On the other hand, 3 years later, we see a claim that overline may simply be applied to any syntactic object. So that author would write the same thing by writing an overline over the whole expression, not separately over M and sigma. Okay, but this introduces a problem. We'll get to it in a moment. In 94, we see the first use of nested overlines. Ooh, what does that mean? Computer scientists always generalize. In 96, we see the overline notation taken for granted, but an explicit statement of convention that had been assumed for about 20 years up to that point. We implicitly assume that when we write something like Z overline / Y overline, that the 2 sequences have the same length. They are constrained to have the same length by the very fact that they are used in the notation in this way. And the next year, we see the first general statement of the idea of pointwise extension. By abusive notation, operations on singletons are implicitly extended pointwise to sequences where those sequences are indicated by overlines. And this is where we run into a problem. The problem is, what does this expression up here mean? Gamma of a bunch of b's equals a bunch of p's with the substitutions applied with a bunch of t's and a bunch of x's. What does this mean? Well, if we apply the principle of pure pointwise extension to both the substitution notation and the equality notation, then this single concise statement up here, remember concision is important, that single concise statement stands for a conjunction of equalities such as gamma of b sub 1 equals t sub 1 substituted for x sub 1 in p sub 1, and so forth, all the way up to b sub n equals the substitution of t sub n for x sub n and p sub n. But unfortunately, that's not what the authors intended by that notation. What they really wanted was this more elaborate conjunction at the bottom, where the b's and the p's correspond and have to be the same length, and the t's and x's correspond and have to be the same length, but it might be a different same length. And the intent is to use the same substitution in all of the equations, where each substitution is multivariable, rather than each substitution having a single variable and a single expression. That was the intent. But somehow the notation didn't quite capture that. So what's going on there? So a solution is nested overlines. Some authors would instead have written it this way, to indicate that the t's and the x's go together, the b's and the p's go together. This seems natural, but how do we know that the gamma doesn't also get subscripts? Because we've got this tension. And finally, we arrived at an essential contradiction. In about the last 15 years, we are seeing many papers wanting both of these usages. We want this kind of substitution equation with a double overline to indicate this conjunction where the substitutions are all the same, and v and x are the same length, but represent the same substitution in each equation. But on the other hand, we also want to describe a case construct where we have a bunch of case clauses. Each case clause has a bunch of variables. We want different sets of variables y in each case clause. And in fact, those sequences y might be of different lengths in each clause. And with a purely syntactic theory, we can't have it both ways. We have an essential contradiction in the notation. And this is the crisis I think we've come to. And so I have a proposal for solving it. And inspired by the consistent substitution convention, actually, and I propose to borrow an idea from quasi-quoting. In Lisp, back in the 1970s, and in Scheme, there was this idea of writing an S expression with a back quote before it to indicate you're pleased to make a copy of the following S expression. But places marked by a comma say except here. What follows the comma is an expression whose value is to be used in the copy instead. So here this means make a copy of this lambda expression, but the variable vars and the variable body themselves have values that are to be stuck into the copy. This idea was also used for parallelism in connection machine Lisp, a language that Danny Hillis and I designed in 1986. And in this notation, alpha marks an expression that is to be executed many times in parallel. So it means execute many copies of the expression, but the bullet indicates except here. The value of the expression following the bullet is a vector, sorry, a one-dimensional array. So please use a different element of that vector in each copy. So here this means we've got a bunch of temperatures, and we're going to multiply each temperature by 9/5 and then add 32, thereby doing the usual Celsius to centigrade to Fahrenheit conversion. So the point is that the idea is to have an expression of which you're going to make a copy or many copies, but you have a way of marking exceptions. Well, now look at the overline notation. What the overline notation is indicating is the stuff under me, please make many copies. But we want to control what the relationships of those copies. So the proposal is that in computer science metanotation that the overline over stir means expand any number of copies of stir. They might be comma separated or something. That's a separate part of the convention. And each copy may be expanded differently. In particular, BNF non-terminals in the copies may be expanded differently. To put it yet another way, in each copy, each BNF non-terminal is given a different subscript. And because it's decorated differently, it may expand differently. But we will use an underline to mean except here. Underlined portions of the stir must be expanded the same way in each copy. And with this simple convention, we can write both of these two examples. For the substitution example, we simply put an underline under the bracket part of the substitution notation. It means that part has to be the same in each copy. That, in turn, contains an overline and then causes it to get a bunch of v's and x's. but the substitution will be the same in each copy. On the other hand, for the case clauses, we write the two overlines with no underline, and that indicates that y may be expanded differently in each copy. And for our third example, where gamma of b equals t/x substituted into p, we use the overlines in the same way, but again, the underline is used to indicate the same substitution in each copy, and an underline is used to indicate the same gamma in each copy. So gamma doesn't get subscripts attached. And this seems to cover about 90% of the uses that I am seeing in computer science papers, and the other 10% would have to be covered by more explicit use of subscripts rather than trying to use the very concise overline notation. I think underlines would do the job. OK, now let's look at ellipsis very quickly. I only have 2 slides to say about ellipsis. One is that it's not well defined. I have not seen a single computer science paper that has actually stopped to describe what this notation means. And here's a quote. Most readers will encounter the ... notation already. It is a notation that is rarely introduced properly. Mostly it is just used without explanation, as in, for example, and here's the example. And the intent is, that these are all the integers from 1 to 20 being added up. In the past, we've used ellipsis to explain the overline. Whenever the overline is explained in a computer science paper, it is invariably explained using the ... notation. So over bar x means x sub 1, comma, ... comma, x sub n. But what does that ... mean? Well, it gets used in 2 very different ways in computer science metanotation. One is to say, there's some stuff missing here, and I expect it to conform to a pattern. And you're supposed to guess what that pattern is from the 2 endpoints, or from whatever context I provided. But the other meaning is ... means there's stuff missing here, and I don't care at all what it looks like. And unfortunately, those two uses are also mixed in papers and not explained. My proposal is to provide a formal theory of the overline notation that does not use ... in its exposition, and then to explain the ... by transformation into the overline notation. And there's a great formal theory of that, which I don't have time, it won't fit in the margin here. And I could spend 2 hours talking about that as well, but I will spare you. OK, so some conclusions about my investigations. I believe that computer science metanotation is a symbolic programming language with its own distinctive syntax, semantics, and idioms. And I believe it should be an explicit object of study in the computer science community. It's a living language. It's changed a lot over the last 4 notations, and some of its notational ideas have roots that go back for centuries. And we are now encountering problems and inconsistencies because no one is designing this language. It's just that every author in good faith is doing his best to use the language well and to stretch its limits of expressiveness without having any specification to resort to. That this is one central place we can all agree on. So we've now encountered problems with substitution and with overlines and with lack of definition of ... These can be fixed. And I believe we should develop a complete formal theory of the language. I've tried to make a start on that. And I think we should apply the techniques we apply to other programming languages like C and Python to CSM and build interpreters and compilers and IDEs and correctness checkers. We should be able to translate this notation into Coq and other proof checkers, as well as write interpreters for it and have other tools. And there are interesting opportunities for parallel execution of this language. The repetition notations offer obvious opportunities for parallelism. And there may be use for parallel algorithms and associated tools. So that's what I've been investigating over the last several months. And what does this have to do with Harry? Well, in fall of 1974, I took Applied Math 208. And on the left, you can see the syllabus. And on the right, you can see the first page of my notes. And I know that it was Harry that taught it because at the top, I wrote very carefully Harry Lewis and underlined Harry.
Now, is that the appropriate use of underline?
Yes. Why did I underline Harry? Well, because I was also taking Applied Math 207 at the same time. That was being taught by Forbes Lewis. So I showed up for Forbes' class and wrote the professor's name at the top and took my notes. And then I got to Harry's class a little later, that afternoon. Said, oh no, Harry Lewis, and I underlined Harry to be sure that I would pay attention. And Harry was at pains to point out that Applied Math 208 was not the same as Applied Math 207, nor any of several other courses. One was a theory of computation course, but the Applied Math 208 was a little bit of Turing machines and then propositional calculus and predicate logic. And you can tell from my notes that I was a very diligent and attentive student. Well, some of those notes are actually good notes, I think. But I want to show you the notes I took at the second and third classes, he started off by talking about Turing machines, and somehow I got it in my head to call them tuning machines. Just because I was feeling silly. And then I wrote out a little tune, which I didn't remember. When I tried to sing it, I realized it was love divine, all love's excelling joy of, and then I ran out of paper. Okay, so that's that little tune written there. And okay, that's probably about all there is to say about that. But in this next set of notes, more about tuning machines, and I'm still silly. I was taking a course in ancient Greek that same semester, so you can see I'm practicing my Greek alphabet in the margins. And so here's a description of Turing machines. What I want to draw your attention to here is that I'm using a highly abbreviated notation, in order to take my notes quickly by hand. You'll notice I always abbreviate the word theorem as THM. And I use the upside down A and the backwards E liberally as a abbreviation. So for all Turing machines M, there exists a Turing machine M prime such that yada, 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 yada. And we see more of that on the next page. On the next page, you also see a reference to Church's thesis. In the margin, I've drawn a little church that is labeled Alonzo. There also seems to be a reference to Martin Luther there. I'm not quite sure what that's about. And again, a little further down, you can see, there exist problems unsolvable by a Turing machine. So again, the use of that backwards E to indicate that. Harry was very long-suffering and patient. I liked him, and I felt comfortable with him, and I felt like I could get away with stuff. So in some of my problem sets, I would stick in quotations that I thought were relevant. Here's one from Nietzsche. It is not enough to prove something. You must seduce people into accepting it. To a wise man, nothing is strange. That was an exercise sentence from my Greek class. That's up at the top. Oh, for one of my favorite comic strips, BC. BC says, "You're right, Peter. The world probably is round. I have faith in you. When one has faith, one doesn't need proof." And Peter scowls and says to himself, "Oh, ye of little proof." In other words, there is value in having proof. So I like that quote. And from Walt Cully's Pogo comic strip, Seminole Sam says, "We must take the truth by the horns." And Al comments, "A dilemma." And of course, there's a pun there because a lemma is a horn. And Seminole Sam says, "Right, I can't read it there, I need to read it up here. Right, we're standing with our feet buttered on a pool of ball bearings. The truth is tricky. One man's truth is another man's cold broccoli." I think those are words to live by. Walt Kelly had a way with words. And Harry put up with all this stuff, but finally at one point, I think he reached the breaking point. And when I put up this Latin anagram, quid est veritas, and he wrote, "Where the hell did you get this?" Of course, this line in Latin is attributed to Pontius Pilate, and it has been anagrammed into words that mean roughly, "It is the man who stands before you," or "It is the man who is present here." And where the hell did you get this? Well, Harry, after 42.5 years, I'm going to answer your rhetorical question. I would like to say that I found it while browsing through Samuel Johnson's Dictionary of the English Language, where he actually uses it as an example of an anagram. Yeah, I wish I could say this, but the truth is that I found it in the funny papers. And it was mentioned in Ripley's Believe It or Not. And you can see from the other examples that I pay much more attention to the comics pages than I do to erudite writings. But there's a couple other things. Oh, yes, I was brash, and I decided to present some of my problem set in the form of Lisp code rather than giving an English explanation. So I just wrote at the bottom, "Lisp code is naturally more readable than English algorithms." To which Harry kindly provided a very gentle corrective for certain algorithms, but try describing the theta of 3n median finder in Lisp. And indeed, that is a more difficult problem. So he had just the right amount of pushback to sort of guide me on the path and let me be headstrong in certain ways, as long as I was sort of understanding the material. But here's the thing I want to draw your attention to. I mentioned before that I was using these abbreviations, these for alls and these exists. And that was okay as long as we started talking about Turing machines, and then sort of okay when we were talking about propositional calculus. Then we got to the predicate calculus. And somewhere in my notes, I have this very vivid memory, and I haven't identified it precisely, but I think that it was as I was about to transcribe this line here from the blackboard, as near as I can remember. But I've got this very vivid memory that as Harry was writing stuff on the blackboard and I was copying it down, that he wrote something of roughly the form upside down AX and then some stuff, if and only if, for all X, yada, yada. And I realized I was about to transcribe it in this way. And I suddenly realized, oh, what he wrote was very profound and connected syntax to semantics. And I was about to write a trivial syntactic tautology that had no content. And it was at that moment that I remember really appreciating the difference between syntax and semantics, understanding the difference between notation and its meaning and their very subtle connection. And so that is my memory of that course. And so I want to thank you, Harry, for teaching me some very important things about notation and about logic and about truth. Thank you.
So it is a particular honor for me to introduce our next speaker, who is my dear colleague, Stuart Schieber. The original title of his talk, which was equally appealing to the real title, was The Trouble with Harry. But instead, we're going to hear about WWHD.
It's just a wonderful honor to speak to you all. Just want to make a few brief remarks between now and the break about Harry. And many of us who teach computer science actually use a simple maxim for guiding our actions as instructors, advisors, and mentors. That is, WWHD, what would Harry do? I thought I'd describe a few of the principles that follow from WWHD as I understand them, that I've adduced and many of you also have over the years, and you know who you are. Many of you are speaking today. So the first and foremost principle is to care. Harry cares about teaching in all of its aspects and has from his first days on the faculty here. Here's a representative comment on Harry's teaching from the Q Guide, noting that the students gave him extremely high overall evaluations, which is not surprising given that Professor Lewis makes an earnest attempt to teach, leading to lectures that, though a little too simplistic, are entertaining nonetheless. Now, what's most surprising about this evaluation is that it was given in 1976. This was the evaluation of the first course Harry taught, perhaps after a grad class one semester, which was NatSci 110 in fall of 75, 76, I think was it. So this never TF'd before, even. First time giving a class, 4.33 instructor overall Q Guide rating. So he's clearly a natural. Now, as Guy Steele implicitly pointed out in his talk, precision in writing is a kind of caring. It shows you have the respect for your reader to sweat the details, to make sure that every aspect is carefully worked out and interacts properly with every other aspect. And by way of example, here's Harry's book with Christos Papadimitriou, Elements of the Theory of Computation. Well, this is your copy of the book, but this is my copy of the book. When I took AM 108 from Harry in fall 1979, he handed out chapters of the book as they were being completed, and he allocated time at the start of each class to solicit errata from the students from the reading for that day. And I marked up my own copy, this copy here, with the errata that I found throughout the whole book. And so I just took some time recently to go through my copy to find all the marks that I'd put in this book, this first draft that he was distributing to his class. And I found 15 marks in the entire book. I'll give you a little bit of an analysis of them. In the 465 pages as they were published in the published version, I'd made 15 marks. Of these, 7 were typos, relatively benign typos. I did find 6 that were what would be considered actual errors. That's 13. And the remaining 2, I had carefully corrected things that were not errors. So, my bad. Sorry. Here's the sad part. One of the corrections actually made its way into the printed volume. So, I apologize. I probably pointed it out in class, and Harry just marked it down, and So that's 13 errors in 465 pages of the public draft. So that comes to something like 1 error in every 35 pages or something, which is an unbelievable rate of accuracy, showing once again that Harry really cares. And it's something that I, too, have internalized this interest in really. The first chunk of that book goes through all of these notational issues that Guy Steele was talking about as well. So that's the first principle, I think perhaps the most important principle that follows from WWHD, is just to care. The second is to promote character over knowledge. Knowledge is really secondary to character. You see this in the title of his book, Excellence Without a Soul. I talked to one, just by way of another example, I talked to a member of the Harvard College staff who was appointed by Harry during his tenure as dean, and she mentioned that Harry hand wrote and signed all of the staff salary letters in the college, which I just found to be amazing. Unfortunately, it turns out he has exceptionally poor handwriting. So this poor woman went an entire year not knowing what her salary was. Because she was too embarrassed to ask. You see it in this, this quote from his memo that he wrote, Slow Down, Getting More Out of Harvard by Doing Less. It's a wonderful, wonderful memo. If you haven't read it, you really should. Offering suggestions about how to get the most out of Harvard. And one of the things he says is that college is a transition period. We'll give you grades and transcripts and so forth, but many of the most important and rewarding and formative things you do will be recorded on no piece of paper you take with you, but only as imprints on your mind and soul. It's really knowledge secondary to character. I still distribute copies of this memo every year, first thing to all my freshman advisees. Whether they read it or not, I don't know, but I think it's important to do so. And the third and final principle I'll talk about is pursuing the right over the popular. More important to do the right thing than the popular thing. Again, in this wonderful Slow Down essay, you see an example of this in the kind of corollary. Don't answer the question the student asked, but the question the student should have asked. Might be more popular to just answer the question, but no, you should think it through. What's really going on? Harry gives the example of a student who asks, how can I do a joint concentration in music and English, when the student really probably wants to know, how can I keep my interest in literature and music alive simultaneously? This is a very important point, and I'll give you another example in a bit, but these are the three main principles of WWHD that I'm talking about. Of course, there are many others, and we learned them from Harry every day. Now, you may think that WWHD places Harry in a kind of messianic role. I have learned the limits of these principles as I've attempted to practice them in my own life as a professor here, and I'll tell you a story that conveyed those limits most clearly to me. Several years ago, one of my advisees, my concentration advisees, came to me early in his junior year, and he was asking about how he starts the process to use his advanced standing status to finish in 3 years. So ask yourself, WWHD. You don't answer that question. You ask the question the student should have. You answer the question the student should have asked, but first you have to figure that out. I channeled my inner Harry, so I had to find out what the real question was that the student had. So I asked him, what's the big rush? Why do you want to finish up this year rather than staying for a 4th year? I told him it's not a race. These are words I was probably just quoting Harry. I mean, it's not a race, that your years at Harvard are a scarce resource. But he explained to me in reply that he wanted to go to Africa to serve as a missionary. So I said, okay, but how about staying for a 4th year, and then you can go to Africa I'm guessing it'll still be in need of your services after your senior year. And his response was, well, I thought about that, and I prayed on it, but God told me that I had to do it next year. So I know my limits. I can't trump God. I suspect Harry can't either, though I have no direct evidence on the matter. Okay, those are all my comments. But by the way, for those interested, I'm taking orders for the wristbands. Find me during the break. Thank you, Harry.
Let me briefly introduce, we're here for the panel session. I'm Michael Mitzenmacher, a former student, TA, and mentee of Harry Lewis. He's served me in all of these roles, and I'll be leading the panel where we'll be talking about various aspects of education. We've brought together a collection of both professors and P and not professors, the NP, for this panel. This is a P versus NP panel that we're having to discuss these matters of education. Their bios are all in the handouts you have, so I'm just going to briefly introduce them by name and get to questions. My plan for the panel, for which we have about an hour and 10, hour 15 minutes, is that for about the first half, I have some guiding questions to try and juice the discussion that I'll ask the panel, and the panel will comment on. You don't all have to comment on each question. You can just comment on the ones you want to, and I'll try and keep you to like a minute on these initial questions. But then what we'd like to do, all of us would like to do, is open up, once we have some of these questions or ideas out there, to open it up more to all of you to ask questions about education that you find interesting or concerning, and hopefully what I provide will be a short springboard to that. Let me start by introducing our panel. Over at the far end at the professor side, we have Lynn Stein from Olin. We have David Malin here from Harvard, and we have Eric Roberts from Stanford. On the not professor side, we have Jonathan Katzman from Minerva. We have Hannah Bloomberg from the Khan Academy. We have Ali Partovi from Code.org, as well as several other things. All right, so let me start by let's cheer the panel. Thank you. All right, so let me start with a question for the panel that, I, of course, sat in on many of Harry's lectures. And I had noticed that recently Harry had changed some of his teaching for one of his courses. For CS20, he's adopted what's called the flipped classroom style, where students actually prepare ahead of time by watching a lecture or otherwise preparing material, and then they come in and actually work out problems in the classroom time, as opposed to the standard lecture format. I admit I am teaching this semester. I have a large class, and I still use the standard lectured format where I stand up there and present the material to the students. And so I'm hoping that all of you will explain to me, what am I doing wrong? What should I be doing? Like, clearly, I guess this is no longer the way. And how should we think of lectures versus non-lectures in the university environment? What should I really be doing?
I note that you're looking straight at me.
I'll start with you, Lynn.
I think the question of whether you're doing something wrong really depends on what you think it is you're doing. What is education for? What is CS 121, if that's the class you're talking about? What is it? What is its purpose, and what are your goals? The lecture comes out of the idea that the goal of the university is preservation of knowledge. Eric Mazur likes to say that it's a really nice way to transfer the contents of the professor's notebook to the contents of the student's notebook, possibly without touching any of the systems in between. I actually think there are lectures that are considerably more than that, and as a student who benefited from many, many lecture classes, I think there's a lot that can happen in a lecture other than copying the notebooks. At the same time, lecture takes everybody in the room and say an hour of 150 people's time. And in 150 person hours, one person is broadcasting. And it's 150 synchronous person hours. We've gotten you all into the same space. We've taken the same time. Is that the best possible way we can use that time? And the answer to that question depends, again, on what you're trying to accomplish. So a flipped classroom takes the premise that what I'm trying to accomplish as an instructor is to give the students an opportunity to form their own knowledge, and I'm setting up that time when we're co-present to make the best use of what we each bring into that room. There are a lot of other models as well, and many of my colleagues on this panel and many of you have tried a whole lot of different ways, but before you can answer the question, is that the right way or the wrong way, I think you have to ask the question, what are you trying to accomplish, and how can you best use the different kinds of resources you have?
So first I would just like to pose to do active learning here. Who's fallen asleep in a lecture? Let's be honest. All right, so this was a quotidian experience for me, I think, at Harvard. Sorry, Margot. Sorry, Harry. Sorry, Rest Retriever. One of the things, so at Minerva, and I could tell anyone who's interested in Minerva about it later, we teach all in small seminar, also fully flipped classroom. And based on the science of learning, and this is the thing that is really amazing and answer this question, is there's like effectively scientific proof that lecturing is by far not the best way to learn. It's an amazing way to teach. As a teacher, you could teach to 10 people or 1,000 people. You actually only still need one teacher. It's fantastic for the university. But as a learner, it's really not good. And there's two basic principles that we always rest on. So one is if you are actually going to learn, you need to do depth of processing. So yes, writing notes is one form of processing, but you need to be actively engaging with the material. And as Lynn just said, if you're actually doing a project or working on problems together, it's a much deeper way. Secondly, you need to build on systems you already know about. You need to attach that learning to something where you have a small toehold already. And that could happen in a lecture or it could not. It's sort of a separate, that's more around the curriculum design. So we at Minerva have taken that to be like everything is small seminar, everything has to be active student engagement, fully flipped classroom. In the last story I'll just quickly tell on this, when I was talking to Harry about Minerva and he gave me the wise advice to go there, he told me the story of changing the classroom, I think it was in Pierce, the library, where he said, I think it was roughly $20 million that it cost to rip out the library, I don't know, some huge number, to basically put in these like very advanced technology, which is tables and chairs with wheels. And so I love that picture of, you know, at Harvard, in order to try this new technology in classrooms, you needed to spend a bunch of money to rip out the library and put in tables and chairs with wheels.
If I could just jump in with very quickly, I think there are some issues with the lecture format, as you mentioned. I mean, I'm fairly comfortable now speaking in public, but I would say if you had asked me to do it, you know, a certain time earlier in my career, it would, you know, give me butterflies in my stomach. And so there's that, and the whole kids falling asleep, you know, it kind of puts a lot of pressure on the lecturer to do things that are separate from learning just to kind of stay exciting, you know, like come out in a bunny suit or something to like prevent people from falling asleep. But what I would say, I really liked what Lynn said. I would actually rephrase it slightly stronger, I guess, which is I would say that prior to certain technology, the lecture was the best way to, you know, to impart a lecture. Now you have the option of just watching it on video, and then that begs the question of, is there no better use of that time? And if there is any better use of that time, you know, of everyone here being together, then you are probably better off having the lecture be watch a video at home and then use that time for something that is a better use. So if you're unable to think of any better use for the synchronous time of all those people, then I guess the lecture is, then you're not doing anything wrong. You have found the best use of that time. But if there's any better way to engage the audience, the lecture is not the best. So.
Oh, no. David, go ahead.
Well, and I think to ascertain whether you're doing something wrong would be to ask not just if students are coming, for instance, to lectures, especially if it's filmed, but are they not coming and are they not watching? Because in our intro class, CS50, which I now teach, was a descendant of NatSci 110 and AS11, students have been decreasingly coming, and we as a class have been increasingly embracing this. And indeed, this past year, for the first time did we very explicitly ask students, come for the first lecture, come for the last lecture, but we don't expect you to come for any of the ones in the middle. And this is in part driven by my realization over time that as much as I enjoy lecturing in the class experience, and while as much as I think we can inspire, hopefully, some of those times, that first time, that last time, I'm not convinced we can do it 26 times, 2 times a week, for some 13 weeks. And an interesting data point for us was 2 years ago, we rolled out this experiment with Yale University where we have a sort of equivalent student body in New Haven experiencing the course largely from afar. We film the lectures, they watch online, but we have local sections and office hours and more in both of these cities. And as a side effect of this experiment, we realized in fall 2015, when we held our first lecture at Harvard as usual, but we held our second lecture at Yale and streamed it in the reverse direction back to Harvard students, we sort of accidentally conditioned 100% of Harvard students in CS50 to experience the class online. And that semester, we saw a marked downtick in physical attendance at lectures thereafter, even though the lectures thereafter were at Harvard. And we went from an equilibrium of maybe 30, 40% attendance to 15% as early as the second or third week. But when you look at the data, upwards of 70% plus of students were nonetheless watching online, which I dare say is a better experience in many cases for the simple reasons that you can pause and fast forward and rewind and review transcripts and all of these digital enhancements. And so to the question of whether you're doing something wrong, I think it really is not necessarily a bad thing to be lecturing and engaging students in that way, but the venue via which they engage with it, I think they have multiple options now.
I'm, I think, the oldest of the college alumni here, and so therefore I have to take the older, more conservative position. I don't think you're doing anything wrong. I've heard President John Hennessy, a computer scientist, just left the presidency, say in public on several occasions that the lecture is dead, even though in his department, lecturers don't lose those people. I mean, yes, we're on quarters, so it's a little shorter, so we don't have to quite sustain the full semester. But people come and they are convinced to go into computer science because of what they see modeled in the front of that lecture room. We put the best teachers we have ever seen in front of that lecture, not because that's the right way to engage students and convey material, but because that's the way to model an excitement about the material and get it shared, to model that education with a soul, because it's a person up there. Just for all of the people who are very concerned about it, no one is going to give lots of money 30 years down the line for their online class. You know, it's just not going to happen. When we ask students why they major in computer science, and 20% of Stanford students are now majoring in computer science, the universal answer, I can't stress this enough, is that they came in thinking they were going to do something else. They took those introductory classes, they took our introductory classes, and they decided to major in computer science. Marissa Mayer, who spoke at my graduation party earlier this year, she took the course for non-majors, got excited by that, and then took the course for majors. We are in the business of being evangelical about what we love. And I don't think that that comes across as well. I mean, of course there are reasons to use all these other technologies, and we use those too. I mean, the point is that it's wrong to think that the lecture is where people learn the material. They learn it when they're actually doing it on the assignments. And so we staff the cluster where students are working 70 hours a week so they can always get that help. That's, the lecture is for something different. If you want to convey material, at least ever since Gutenberg, we've had a model for doing that. But that's not what the lecture has ever been for, and it's not what I think you can do with it. And you know, I think that there's room for all these experimentations, but don't throw the lecture out. It's way premature.
I guess speaking directly to CS20, since I was a student in TF for the class twice, I do think you can capture a lot of the excitement in a flipped classroom, even without the lecture. Since you're working in these small groups, we pair one TF with about 4 to 8 students. I felt like I got to interact with those students even more than I would have if I were standing at the front of a section. And to try to convey my excitement for not only the material, but also the process of working from problem to solution.
All right, let me go.
Can you guys address how distractible devices affect
Does anyone want to take that? Have distractible devices?
Can they pay attention long enough to really do it?
So,
I'm sorry, I wasn't looking. Could you repeat the question?
Lecture when it's at its best, I think, is very much what you were talking about, Eric. Lecture is good theater at its best, and it does the things that theater does for you. And when I go to the theater, I don't get distracted by my cell phone, partly because they've made me turn it off, but partly because when I go to the theater, it's usually really compelling, and I'm not drawn to the devices.
But you're not a student.
I'm not a student, it's true. I think if your purpose is to have a broadcast experience that's genuinely compelling, I think it's possible to get around the distraction. I think the problem is that often lecture isn't understood to be a broadcast experience which has to be compelling in all the ways that Eric, even hearing you answer that question, I know why your students feel the way they do. Unfortunately, not all of us have those gifts, and I can tell you that for me, what I mostly want to accomplish in my classroom is not something that I think is best accomplished by my standing in front of a large group of people and broadcasting, because I don't have Eric's gifts. So in that case, I have to deal with the what am I trying to accomplish, how am I using it, and then how do I avoid distractibility. Actually, for me, the devices are often an asset because what my students are doing is individualized, customized, small group work so much of the time that they're actually using the connectivity as an asset in their face-to-face work. But that's very different from a lecture experience.
Again, I'm willing certainly to have more questions. Yeah, we'll get through some questions first, but if anyone has an immediate question they want to ask related to that, we could probably take one or two more and then move on. And yeah, Al.
Isn't there something more, though, that we can do with technology beyond video and beyond, Eric and his most wonderful projection? Isn't there something we can do that would make essentially this less?
We're doing lots of things with technology. I mean, I think some of the most exciting projects that I've seen in recent years, Chris Peach is one of our faculty, and his doctoral dissertation was on using traces from all the different versions of code that people produced in the introductory class, do machine learning on that, understand where the clusters are that represent areas where people are confused, and then use that to figure out how to move people and do those things online at the same time. As we've built our own tools, collect those data, and be able to apply them. I mean, the technology gives us tremendous opportunities. Technology has improved the lecture since I was lecturing in that Sci 110. But it's all, I think, really about caring about those students in some ways and making that demonstrable in everything you do. So I'm not in this instance a Luddite, I am in some others, but I think you can use it very well.
Yeah, and I think to follow up on that, there's also this tension between online versus offline, lecture versus not lecture, and I think you have to look at more, what is the mode in which you're teaching, what are you trying to do? Are you trying to do project-based learning? Are you trying to do seminar? Are you trying to do flipped classroom? Technology be brought to bear in many different ways across all of those, similarly with what they're doing just in students' homework offline. So you really need to think less about am I lecturing or not lecturing, and what is the purpose of that, and more about, again, what am I trying, and what is the learning outcome for the student, and what's the best way to achieve it? So.
Gary.
I just want to throw in a comment. It depends a lot on the course material. I mean, Lynn asked the right question.
Right.
The answer to Lynn's question is not the same for every, for every course. So the flipping works very well in CS20 because the course material is so modular. And in other material, the lecture format with the right lecturer is going to still, I think, be superior. But I just want to add that one of the great advantages of the flipping is that the professor may not even need to be in the classroom. So, for example, I was able to teach CS20 quite successfully from 10 to 11 this morning. Michelle Danoff over there in the corner, who was one of my undergraduate teaching assistants, ran the class just fine without me. So, thank you, Michelle.
Right. Well, let me ask one or two other questions that cover other things, and I'll allow people, will certainly come back to these things after we first. I also like the idea that maybe we'll just have Harry answer every question after the panel as we go through the. Okay, Margot. She's my boss.
Because I so rarely disagree with Harry, I'm gonna disagree a little bit, which is that even things that are not modular can be flipped very effectively. So what Jonathan and Ali didn't tell you is that one of the courses where they regularly fell asleep was in fact my operating systems course, because they had been working all night, as Hadi explained to me.
Yes.
And I have vivid recollections of one class where they were like totally sacked out in the middle of Pierce 208. And I was going around the room like asking people to contribute parts of questions, and they were like out. Anyway. But that is a course that is incredibly not modular in terms of concepts, and yet it turned out to be a very effective course to flip, because the challenge in that course is really translating the concepts into code. And where most students spend those all-night hours is in that process. And if you can jumpstart them in the classroom doing that, believe it or not, it actually does save them some time in the long run. So I think modularity may not be the only thing that makes flipping practical.
Let me take a different question, because I'm going to try and hit a couple different levels of scale or scope in the course of this. And so this is maybe a similar related question, but at a different level. So Harry's career, of course, has been deeply tied to Harvard University. He's not only led the computer science department and temporarily C's at various points in times, but was the undergraduate dean for Harvard University for many years. And as we've seen in the last question, we're increasingly seeing more and more technology, online courses, tools, offerings, and so on, that many people argue reduce the need of the traditional university to be what we think of as the home of learning. And so we've seen technology wreak havoc across many other fields, many other institutions, the press being one of the most notable ones. So as technology continues to work its way here, what should we think of the role of the university being in the future? And how can institutions such as Harvard adapt to these changing means and methods of education so that we can continue to survive and hopefully thrive? Same one.
I get asked this question all the time. Sorry, adjusting the mic here. I get asked this question all the time. People are like, aren't you disrupting universities? Do you want to see all universities destroyed? And it's just like unequivocally wrong and not our view at all. And especially the top universities, we expect them to remain the top universities, and we happily will hire all of the PhDs you produce to teach our undergraduates. So we appreciate that. And so I think, again, there's a question here less of what is the purpose of the university, and more if you're going to spend $60,000, $70,000, and especially I think this is, again, not going to be an issue for the top 10, 20, 30, I don't know, universities, but for, say, number 50 through 100, I think a lot, and I hear this from parents now, people are really starting to question that value. And so that's where I think you're just going to see a lot of other tracks for certain jobs go other ways, software engineering probably being one of them. And it could also be nurses, paralegals. There's lots of jobs that could take the boot camp model and do very well with just a year or two of post-secondary education. So I think that'll be very interesting. And I think the biggest issue with universities that we see is, like this university, there's a lot of focus on research and really understanding the balance of research versus undergraduate teaching. I think I would love to hear some of the professors' view of that. That to me is like the biggest split of really where university can be focused.
One of the professors want to respond?
We saw in Guy Steele's notebook this notion that, in fact, the things that you learn at a university are mostly the things that you learn outside of the classroom. We come together in these academic communities to experience each other, to learn from one another, to have this experience, which is almost impossible to have in other places, to get out of that insularity, to try new things. I've been extremely fortunate at Stanford. I've had the chance to teach courses listed in 17 different departments and programs, from English to history to computer science to science, technology, and society. You just name it, you know. It's just, I found a place where somebody wanted to teach a course with me, and we did it. And it's been amazing to have that old style. You know, I was telling Harry the other day, I've been living in Oxford, England for the last 15 years. It's the first place I've ever felt like I was at home, you know. It's been there for almost 1,000 years. It's, you know, people have been doing this kind of thing and making tremendous progress for society because of what we as academicians and as communities of students and professors and everyone else who's around the university does. I believe that that's the future of universities, and I worry mostly about sort of the faddishness that comes along with each new technological marvel. In the Senate, faculty senate at Stanford some years ago, maybe 6 years ago, there was a panel on MOOCs right after, you know, MOOCs became popular, and every single panelist, you know, was in favor of MOOCs. You know, ran the gamut from A to B. You know, it was not exactly a balanced panel. And then 3 years later, if they didn't have another one on flipped classrooms, where they began by saying, well, you know, MOOCs didn't work out, but here's a panel on flipped classrooms, which had exactly the same range. And no one saw the irony. You know, it just was, you know, we have to understand that universities have contributed something, and I think a lot of people in universities understand that. But there is this call, and there's this pressure from industry, from parents who don't understand that, you know, places like Harvard and Stanford are going to fund their children's education if they can't afford it. I mean, you know, we got to get that out, because it's so transformative to be able to go into, you know, I'm a hereditary academic, so I got this from, you know, from day one, but a lot of people don't have the advantage of growing up in a family where books and ideas matter, and at least for 4 years we can give them that.
Does anyone else want to comment on this? Or questions out from the audience? Yeah.
Is that an either or? Because I think it really is both. So I feel like I have only one question, and it's, what is the purpose? So what is the purpose of a university? And I actually think historically universities have had a lot of different purposes, and we're seeing some of those purposes come into tension in new ways recently. And I think that's part of why, you know, as long as I can remember, there's been the crisis of university education, but I do think it's gotten more acute in some ways, and I think in the next 30 to 50 years, this landscape will have changed. I don't think in the next 5 years this landscape will have changed, in spite of Minerva's best efforts, or Olin's. So the university, you know, from the perspective of a student, is it education? Is it training? And I say that not in a pejorative way, but in a empowering me to go on and do the next thing, empowering me to the next stage? Is it finishing school? Is it a community, a respite, a place to grow and mature that's where it's a liminal space that's not your parents' home or your childhood, and it's not your fully independent adulthood either? And then, of course, that's only with respect to students, but there are also questions about, is the university about preservation of knowledge, which historically, I mean, that's where Bologna came from. That's where Oxford came from. Preserving knowledge in a time of uncertainty. Now I'm pretty sure that everything that exists now is going to continue to exist in some way, shape, or form electronically forever. The question is finding it. It's not, I'm not worried about preservation. I'm worried about understanding and use, but preservation actually feels pretty good. But maybe the university is about creation of knowledge. That's a different thing. And that used to be really tied to that educational piece, and now it's not clear whether that mooring is coming uncoupled. Or there's the sanctuary space, the place where people can think about things that are very far in the future and not just what's going to happen tomorrow. And all of those are jobs the university could do. I don't know that all universities can do all of them, or even that any universities can do all of them. I think we're at a moment where we're starting to disaggregate some of those questions. And unfortunately, we're not able to design clean slate mostly. It was lovely to have that opportunity. Though even in Olin 17 years ago, when we were literally a hole in the ground, it turned out it wasn't really a clean slate. There were really a lot of structures and constraints in the world. But the finances of how universities currently run, which is different from how they ran 100 years ago, and which is different from how they ran 300 years ago, and will be different in 20 years or possibly sooner, depending on politics. How do we explore what it is we want to be about, and then find models? And the people on this panel are all in different ways exploring alternate models of how we can accomplish some of those jobs. And I do think, because the university, Harvard, was created about preservation, it is harder to change things at Harvard. And yet, those of you who read my bio may know that I taught. Literally, Harvard could not find a space, physical space, for the class that I brought to Harvard the semester I was here on sabbatical. I was teaching in an atrium. The Pierce renovation happened within a couple of years and is a space that would have been a lovely one to have. This building contains spaces that changed as a result of conversations that happened that year. And I've seen plans for what might be built in Alston, which is already beginning to change. So even Harvard is capable of change, which gives me enormous hope for what's possible in the future.
Okay. Let me go on to another question. Take a slightly different area. So Harry's grandchildren are arguably just a bit too young to be starting to teach them computing. You know, arguably, maybe they're ready now. And I would say, I think historically, teaching of computing, not just coding, but all of computing, at the K through 12 levels, in the United States in particular, but also around the world, has been sort of at best minimal and haphazard. And yet, somehow, out of that, I work on admissions with Marlon and Harry. I see Harvard applications now with students doing things ranging from building simple apps that are being used at their schools, to building websites, to doing research using AI to find better ways to diagnose cancer, even without some sort of formal training. One thought or one feeling is that seeing that makes me feel we could be doing so much better if we actually had a better developed, more standardized formal system. So for the panel, how should we be thinking about teaching computing at these K through 12 levels? Should computing, like math, become part of the standard curriculum? How could we make that happen, and what would that look like? Do we actually think that some type of standard program would be a help, or is the diversity and fast pace of the computer field make it so that standardization of a program would actually be a bug rather than a feature in terms of teaching at these levels?
So I'm gonna take this one because Code.org is essentially. Actually, I'd love to ask how many people here have heard of Code.org or the Hour of Code. Okay, so I actually take issue with the suggestion that computer science is haphazardly taught. I think that would have been very accurate if you had said that 4 years ago when Code.org was founded. 4 years ago, only about less than 10% of schools in the United States offered any form of computer science at any, one AP class or so on. And only 9 states in the country accepted it as satisfying graduation requirements. Something like 2% of students took it. And the vast, 90% of students didn't even have the option to take it. Today, and largely due to the work of Code.org, but also partners that we work with, 10% of K through 12 students on the planet have done coding. 20% of kids in the United States are learning it, which is significantly up. 20% of teachers in the United States, 20% of students in the US have an account on Code.org to learn computer science curriculum. This is mostly K-5 actually, and 20% of students in the United States. Hundreds of school districts have made commitments to embrace it, and some of the largest ones have already rolled out CS to every school in their district. Code.org alone is training about 25,000 teachers per year to teach computer science. So in contrast, there were only about 18,000 teachers in the entire country that taught it 4 years ago. There are now about 50,000 newly trained ones in the last 2 years. So there's a sea change that has occurred already, and about 30 states now and 11 countries outside of the U.S. have officially embraced it in their in the educational policy. What I would say, though, that the key to all this having happened in the last 5 years has been the ability for the curriculum to be fluid. So if it had been via textbooks, it would have been a lot harder to, first of all, it would be more expensive to disseminate it, but also harder to stay abreast with what you pointed out. It's a fast-moving field. So I think a key part of it is that teaching computer science to kids can be done via the web and via interactive, step-by-step tutorials, and then you can see, oh, everyone's getting stuck on screen number 5. There must be an issue that is challenging for young kids. Let's go look at it and see what the challenge is and fix it. And you can essentially tweak the curriculum literally daily to make it more effective. And that's a huge part. I will also say for the youngest kids, perhaps even Harry's grandchildren, I certainly would say that learning how to spell and write English and all the grammatical weirdnesses of exceptions to every rule, that is far more challenging than learning the highly logical and predictable rules of computer science. And as a child, one of the most comforting things is to have rules that don't have exceptions. Here's the rule, and once you learn the rule, you learned it. In English, every rule has exceptions. Literally, there are no, it's extremely confusing and frankly discomforting to kids. In a language like a computer language, or here is the rule, there are no exceptions. Once you learn the rule, you learned it. That provides enormous comfort to kids. I, as a kid growing up in Iran, in Persia, I grew up during the Iranian Revolution, and my entire life was filled with chaos and fear. For me, learning to code was actually a form of comfort, because here was the only part of my world where laws and rules were consistent and were not haphazard, and where I could have something of consistency to comfort me. But I would say that's true for all kids. It's easier to learn an if-then statement than to learn how to form English grammar is actually more confusing. And I would say it makes sense to teach computer science principles before teaching writing and reading. Speaking, obviously, speaking is, our brains are evolved for speaking. But reading and writing using the English language is extremely challenging for kids to learn. And I would say it's, you may not be able to teach them how to type Python code, but the type of code where they drag and drop, icons that say, follow the up arrow or left arrow, or move the bunny this way or that way, that stuff is actually, I think, easier to teach than basic English.
I actually think this is one of the most potentially impactful opportunities for higher ed, especially as this MOOC craze is sort of entering equilibrium, is to focus not so much on trying to teach masses of hundreds of thousands of people, the sort of end nodes of the graph, but to actually start focusing more on uplifting K-12 and some of the inner nodes. Indeed, as we and our team here at Harvard has focused a lot more on grades 7 through 12 and essentially porting our own college curriculum in CS50 to a high school audience, focusing not just on the students, but on putting together more supportive lesson plans and professional development and training programs for teachers. I mean, hands down, that has been what we've experienced to be one of the most limiting factors. It's the math teachers who are the closest thing that the principal can identify to a computer science teacher, and so he or she is being asked to teach Introduction to Computer Science, or the phys ed teacher in some cases. And so the fact that we increasingly have these hopefully high quality educational resources that are full form courses themselves, so that a teacher on his or her own can tune into a Stanford or Harvard or MIT or Berkeley class and has access to not only the experience of being a student, but on the tail end of now, much like our own Harvard tradition of bootstrapping our own courses by teaching students who then become our own TFs. I think we're increasingly seeing that a potentially impactful model where we have our high school teachers taking some form of CS50 or a Berkeley course or the like, and then one semester, 1 year after, are they themselves better equipped, not necessarily fully confident, but can now take on more of a TA-like role in their own high school or middle school classroom, leaning on the resources of a place like this, which to the question earlier about resources, I think is hands down one of the things these institutions in higher ed should be doing as a social good. And then a year later, 2 years later, as they get more comfortable, much like our own graduating seniors, can leaning on us become less of a thing? They can stand up full-fledged, and now we have a full-fledged computer science teacher teaching some program. And so that's what's gotten us, I think, the most excited about MOOCs and online education, is how we can reach the inner nodes of this graph and achieve some kind of exponentiation by teaching the teachers.
Going back to the question of standardization, I think one thing that's particularly exciting about AP50 and similar curricula is the move from AP Computer Science A, which said, oh, you have to learn Java and you have to learn it in this way and you have to, do this grid world project in order to do well on the exam, and then moving towards this AP Computer Science Principles, which is based on things like, understanding critical thinking and problem-solving skills and creativity, and it's completely language agnostic. I think that's like a really awesome thing to be able to move away from, it's important that you learn Java, to it's important that you learn these computer science principles, and then later you can plug in any particular syntax in order to achieve those goals.
If I can actually just riff off of that, I think one of the most important factors in kind of thinking about this is to extract the word code or coding from computer science, and actually, because my organization's name is code.org, it's a blessing and a curse, because there's this whole learn to code movement in schools, and the reality is, it is not about learning to code. In fact, the least valuable part of it is the coding part, and also the most likely to be irrelevant. If you learned Python, like 8 years later, it'll be, kind of no longer useful to you. The two things you really are learning, and they're different, one is computational thinking, and logical thinking, the ability to, understand a repeat loop, whether it's called repeat or for or while, or, that doesn't matter what the code is or the language is, but the idea that I can instruct this device to do this repeated thing, understanding abstraction, understanding functions, that is extremely useful not only to a career as a coder. That's useful if you want to become a lawyer, for example. It's useful for so many different careers, and it's useful for kids, in 3rd, 4th grade to learn those principles, not just, not the ones who are thinking necessarily vocationally. The other thing, the other part is what I would call digital literacy. And I would say it's critical to just understanding how the world around you works. There's a reason why every school in America teaches biology. You know, you wouldn't send your kids to a school. Imagine if I told you that if you have a kid in high school, they are going to graduate without knowing what photosynthesis is, or without knowing what their own esophagus is, because you would not consider that an education. You would not consider a person to be educated if they came out of high school not learning the basics of the natural world around them. Well, kids these days all have one of these things, and they use it much more frequently than their own esophagus. No, it's true. And I would say they deserve a chance to learn how both work, and they deserve to leave them in the dark about how this huge part of their world works. I'd say it's really kind of, frankly, we've failed that entire past generation of, high school kids who have graduated oblivious to computing, and the current generation of kids, we really owe it to them to have them understand it. It's as if we literally, we have entire generations of kids. It's equivalent to having generations who are oblivious to how photosynthesis works, or their own esophagus, or so on. And it's something I think that's almost an emergency to bring up the digital literacy of the population.
I have a couple of cautionary notes. I mean, the work that Code.org and Khan Academy have done has been fantastic. I mean, and I've been a part of the CS Principles project since it started, and I think that that's moving in the right direction. But there are unintended consequences along these lines that I'm not sure that everyone thinks about. And one of those, you've alluded to, I mean, absolutely professional development is the key part of anything that's going to bring it into the schools, because the teachers don't know it.
Agreed, totally agreed.
And I used to ask my class, how many of you took CS in high school? And lots of hands went up. How many of you knew more than your teachers? And most of the hands stayed up. I remember, I don't know whether Harry remembers this, when I came back to Harvard after starting the department at Wellesley, we talked about there seemed to be a little bit of a decline after this giant bulge at the beginning of the 80s. Why is that happening? And Harry's answer was, it's because they started teaching computer science in high school. Not because they learned it there, but what they learned was that they didn't like it because of what it was, and that's, we've seen it replicated all over the world. So it's not enough to teach it in these schools, you have to teach it well. And so that's professional development. I led a project to build a high school computing curriculum for the island of Bermuda with its 2 high schools and 60,000 people about 15 years ago, and its enormous wealth from offshore tax haven status, so they could pay $1 million for this project. And so we were teaching all the students, and we knew that professional development was going to be the right thing, and we also anticipated that what we needed to do was train twice as many teachers as we needed, because half of them would leave. As soon as you teach a high school or an elementary school teacher to code, they have opportunities that pay 5 times as much that don't involve discipline. Well, I suppose those of you who've worked in companies can talk about the discipline problem. But anyway, that's, we can't hire at most universities and colleges in this country people who teach computer science and are qualified to teach it. How can poor school districts get the right people? We have to create them, as is being done. But the other, and I think more serious problem, I've distilled this into a soundbite at various conferences of late, is all of these things are working on the demand side of the equation, because in the mid-aughts, we had this decline, mostly I think generated by this perception that all computing jobs were going to be offshored. Right. I mean, complete lunacy. Oops. But people believed it, and it was the world is flat and things like that. And so even after the industry recovered from the dot-com collapse in 1 year, we kept seeing this declining numbers for what was arguably the best job on the planet. And so how is that happening? So there's been a lot of work to increase demand, and my soundbite is Actions that increase demand without increasing capacity are suicide. Schools are seeing more and more people coming in that they can't teach. I don't like being 20% of the majors at Stanford because we're only 2% of the faculty. And only one of those numbers is going up. You can guess. And if that's happening at the Stanfords of the world, what's happening at the state schools? And I'll tell you what's happening at the state schools. I'm on the National Academies Committee to look at this problem. Every one of them is imposing strict limits on who can major and who can take courses. So what we're doing is we're generating lots of students who get really excited by this. And the first thing that happens when they get to college is they're told, I'm sorry, you can't do that. We have to work on those two problems together. We have to, there needs to be a change. Absolutely. We need to have a new vision of what computer science can be in the 21st century in universities, because it's part of everything. But the model we have for teaching it now is not sufficient to scale to that level.
So I agree and disagree with some of the things you said. I strongly agree that professional development is critical. And Code.org is actually something like 80% of our time and money is focused on that, on training teachers. It is some of the hardest work to do. I also very strongly agree with your presenting it as a supply and demand, and we see it exactly the same way. Code.org's Hour of Code is basically a marketing stunt to generate demand, and everything else we do is to generate supply, essentially. And we create curriculum, we do professional development, et cetera. I think I would say somewhat disagree with, I think that what you talked about, it's not being taught well, I think that is changing. I'd say that, again, I'd say it's more like 4 or 5 years ago you had this issue where there weren't enough teachers or they weren't capable of teaching it well. And I think that that is improving. And I also think because of, in fact, large extent because of Khan Academy and our work, because kids are now learning it in 3rd grade, 4th grade, 5th grade, it's a completely different dynamic of, you know, how much they know and how well prepared they are by the time they get to 9th grade, let alone to university. Where I do think a part of the solution is with the kind of universities' challenges is that computer science, I think, really over time needs to be integrated into all subjects. Certainly in the professional world, there's not a single industry that has not been in some way impacted by computers. In academia, I'd say, you know, not just in university level, but also the high school level and below, perhaps computer science needs to be integrated into lots of other subjects. And then it won't be, oh, we don't have enough CS faculty. It'll be all the other faculty need to learn some CS as part of their existing.
We have about 20 minutes left, and I'd like to open it back up to the audience. I think there are several things to think about. I'll try to sort of do passes around the room. Yeah.
To help with rampant misogyny? Yeah, so this is very near and dear to my heart. And in fact, when we were starting Code.org, we were very seriously considering before choosing what name, we were considering, should we name it something that's focused on women? Should we entirely make the organization be about getting more women to learn computer science? We chose to ultimately have it be kind of universal, but it remains one of our most important metrics that we measure how many girls are doing the Hour of Code. It's 48%. How many girls are enrolled in our classrooms? It's also, you know, steadily at around 47, 48%. And so I think the misogyny has been perpetuated because of the fact that, you know, prior to Code.org, it was only taught in high school, which means it was an elective, and it wasn't a graduation requirement. So it was only really taken by kids who had already kind of fallen in love with it at home as a, you know, from their parents or a camp or something, and those tended to be the white or Asian males. Once it's introduced in, say, 2nd grade, 3rd grade, 4th grade, you know, in elementary school, and all the kids are taking it, then it's no longer perceived as a male or female thing. Like if all the other kids in your 3rd grade class do something, you think of it as just something we all do. And the Hour of Code also, as a concept, was very consciously designed for this. You know, our Code.org actually sort of, our founding idea was there are 3 things we wanted to accomplish. We wanted to help the schools in terms of curriculum, professional development. We wanted to change the rules in terms of education, graduation policy, and we wanted to make computer science cool. The hardest part of all 3 of those was the last. How do you make computer science cool? And especially when the people trying to do so are me and my brother Hadi, who are the nerdiest kids, you know, from our, you know, our own high school. And then we realized the key to making anything cool is to involve girls in it. It's true. And so the Hour of Code, the idea for the Hour of Code was to get entire classrooms or entire schools to say, we are doing the Hour of Code. That means every student in the entire student body will do 1 hour of code. That means the girls also have to do it. And then when you have that, it becomes a social experience. We're all doing it, girls and boys. Literally after that 1 hour, you haven't actually learned that much computer science, but you've experienced doing this thing with the girls, you know, and it now has become something cool, and it becomes something that both boys and girls feel, hey, maybe this is something we want to continue doing. So,
as much as anyone else on the panel want to respond a bit to that?
Well, I think this is one of the most important challenges we have to face. When I left after my PhD at Harvard, I decided what I wanted to do was start a computer science department at a women's college. They weren't advertising for computer science because they didn't have computer science departments. So I just wrote to the presidents, and I ended up at Wellesley and started that department, which is now 35 years old. And that was exciting. You know, 100% of my students were women. That was pretty good. But, you know, at Stanford, out of that 20%, over 30% are women in a field where nationally the number is closer to 17, so it's almost twice. 37% of the new students declaring in the previous 2 quarters, the last 2 quarters, were women. And I think you're absolutely right. I mean, if you do it for everybody, if 100% of Stanford students majored in computer science, with 2% of the faculty, heaven forbid, it would be 51-49. You know, it's amazing how that works. You know, if you just get a larger N, you know, partly because if you are skewed, then the complement of that set is skewed in the other direction, so you're going to pull more people in. But it also becomes something where people feel so much more comfortable. You know, I get these calls from media people who think that that there are only a handful of women, and I have a slide where in tiny, tiny thumbnail images, I just show all 220 women majoring in computer science at Stanford. You know, it's just, that's a critical mass. If you don't have the critical mass, you can't do it. But one thing I think everybody needs to know is that the data on this question are very easily understood historically, that the times when women's participation falls off are precisely the times when universities start to ratchet down the numbers. If you cut the numbers down, participation by women and minorities declines and stays down. And part of the reason for that is because most of these things are competitive. You know, you impose a GPA, or you look for people who are taking the 2nd and 3rd course in their first year, and that biases against people who have been doing it in these high schools where there's a lot of implicit bias. You need to keep those doors open so that you can avoid the last hired, first fired model. And it's just absolutely obvious when you look at the data that there's this, in the huge collapse in the mid-'80s, that's when women's participation turned down. And then you get people talking about this as if, it was violent video games. This is the year the Macintosh was introduced. There were no video games, in that year. That can't be the explanation, right? They're horrible, but that wasn't it then. It was that every school said no, no more. Even Wellesley had to do it, and I left after that. I just, it changed the nature of the program. Unless we can provide the resources that we need to teach all those people and build that critical mass, we're going to lose it again.
Yeah.
Okay, wait a minute. I'm sorry, Michael. We talked about a gender problem, and you didn't let any of the women on the panel speak.
No. If they would like to speak,
I was actually very conscious of that. When that question came up, I figured it was going to be thrown to me, and I didn't want to take it first. And in part, I could talk for hours, for days. Find me anytime. This is a question near and dear to my own heart. I will not give you my stump speech. I will say that the things that Ali and Eric are both doing and talking about are incredibly important. And my plea is, this is a really hard problem. Each of us is contributing to the problem, for sure. I know there are things that I do that narrow who goes into my field, that narrow what people see as possible. And I hope I do more good than not, but each of us needs to work on it. If you are a man, this is your problem, not just mine. If you are white, this is our problem, not just the single face of color that I'm seeing in the room. If you are someone who had a good education and had good resources, this is our problem. If you are in a position of privilege because you were at Harvard, this is our problem to change the demographics of who enters. And it's not just who enters, but it's also who stays. So if you are in industry, this is your problem. Right? And each one of us has to all the time be vigilant about the ways in which we are inadvertently undermining the thing that we actually want. We all have allies who can help us, and if we're willing to listen, if we're willing to hear the things we're doing that could be done differently, we can solve this problem, but we all need to own it.
Thank you. I just want to say I love the way you said that, because when Hadi, my brother, and I started Code.org, we are white, male, privileged from the tech industry. We absolutely created Code.org because we felt exactly what you said. That if we don't do it, if people like us aren't doing it, it's not going to be fixed. I do feel, though, that starting in the K through 5, if you fix it there, the solution will, it's just a matter of time for it to propagate up.
I teach at an institution which has historically been gender balanced since the outset, and let me tell you, that did not solve the problem.
Another question.
But there is a parallel in medicine. Speaking as a physician, when our mother went to medical school, her medical school class, coming out of a junior college and into medical school, she was an exceptionally bright young lady at the time, was about 10% at the University of Michigan. At Baylor, Baylor College of Medicine, where I am now, when I went to medical school at Michigan, it was probably about 30% of the class was female. Now it's about even-steven. It's about 50-50. So something's happening in the medical profession. We won't talk about standards, but that has shifted this balance quite dramatically in about 25 or 30 years. So what is different about CS globally than what's going on in a higher level of education in the biological sciences and medicine? I'm asking a question without an answer, at least one that I have.
Take it as a rhetorical question. Can I?
Yeah.
I just want to, before you move on to the next question.
Absolutely.
I just want to acknowledge that we have the original Wicks, the 5 women from the class of 1980 in computer science. Of course, there was no such thing as computer science, so half of them were in engineering and half of them were in applied math. But they were gathered there in the first 2 rows over there.
I'm not sure if anyone on the panel feels that they have an answer to that question. So if not, maybe I'll move on to.
I just want to bring up one subject that has been touched upon. The Harvard Business has a very famous approach pedagogy. They even teach a course on teaching people how to teach by the case method. Now, when I was on a flash science faculty here before I retired, I actually went and took that course and adapted some of their techniques over to my own course on operation research here. So I just wonder whether there are people who have more experience with this method, or something that if you don't, it's worth taking a look at.
We don't, people are looking at me, but we don't use the case methodology per se, but I do think to go back to the science of learning principles, it's exactly those two things. It's very active, you're engaged with the material, you're discussing it in class, you're discussing it with your classmates, it's building on each other. And then it's also useful in that you're able to have the same section across multiple different faculty, all repeat and actually use the same material curricularly, so that works well as too.
Sorry, Q.
There was actually a fairly large movement to do case studies in computing. Mike Clancy and Marcia Len at Berkeley did a lot of work. There are many papers in the 1980s about it. One of the difficulties with that, with other styles of learning, is how well it scales as the number of people grows. The Harvard Business School admits a very limited class. You know, I have 600 students when I teach the intro class in the fall, and I'm trying to keep as much high touch and being part of their lives as I can, but it's harder, and it's not a question. I got a note from Provost Condoleezza Rice when I was director of undergraduate studies and she was provost, saying that they had decided that every department should beef up its intro courses so that they were taught by faculty in classes of 20 students or less. And I said, fine. You realize that if we took all our faculty with the teaching load they have now, they wouldn't cover the introductory classes. Who teaches the rest? You know, I mean, it's just those numbers, and the university is not willing to make computer science be 20% of the faculty or anything close to that, and I wouldn't want them to. I'm happy to be a little overloaded, but you know, there are limits to that, and we have to find structures that we have found, we've experimented with and have found to be effective that work at scale, and we're using technology to extend our reach. But still, we think that the best strategy is to inspire in the lectures and then have undergraduates, as we do here at Harvard, teach those small sections in CS50. I mean, that's what makes it work. And without that and that ability to really, you know, it's near peer mentoring. You get to see people who are just a few years ahead of you doing amazing things that show that the university places an enormous amount of responsibility. If I hadn't been an undergraduate teaching assistant for NATSCI 110, you know, I wouldn't have had the same experience I had here. Since I'd wanted to be a college professor since I was 5, I think, you know, grew up in that household, you know, I probably would have done that. But John Hennessy, our former president, says that had he not been an undergraduate CSTA at Villanova, he would never have considered going into academia. You know, it really is part of that pipeline creation, the way we do it now. And you know, one of the things that I think I am able to do in those large classes is I inspire not just the students, but our army of section leaders who are going to go on and be the next teachers, the next Harry, the next me, the next David, and next Lynn, everybody, you know. She doesn't have the big classes, but she's got better touch, you know, so she'll get a higher fraction.
This isn't exactly the direction you intended, I think, but we actually have a course that's called literally CS50 for MBAs, and in fact, in about half an hour, I go across the river to teach that, which is a smaller scale course that's more top-down than it is bottom-up. And one of the things we experimented with a couple of years ago was actually visiting some of our friends in industry and actually using technology and video to capture case studies on camera. As an aside, one of the hiccups we ran into is at least our friends friends in industry weren't as willing to disclose some of the interesting teachable moments, mistakes they had made in terms of engineering failures. But today, for instance, we'll be joined by an alumna from HBS, Christina, who's actually now at TripAdvisor down the road, and the whole class in just about half an hour will be a discussion of some of TripAdvisor's experience with deciding on mobile strategies, whether to do applications or websites or so forth. So in a smaller scale group, we've done that, I think, pretty successfully. And to be honest, what's been great about HBS is how they even design the classrooms with the pedagogy in mind. To Lynn's point earlier about the classroom we now have in Pierce, I mean, even a detail like that is important and changes, I think, the dynamics and the interactivity we have. And so it feels very different, even for me, teaching students over there than it does an equivalent number of students in a lot of our classrooms here.
All right. I think we'll do one last question, and then we'll break for lunch, so I can keep us roughly on schedule. David had his hand up earlier way before. I think I owe him a question.
So there's a paradox I've been sensing in some of what's being discussed. I'm not sure I can articulate it well, but I want to try in order to get some responses. It seems like we're talking about this idea that sort of computer science is something that we're sort of struggling to teach in at a university. At the same time, it's something that can be taught in third grade, and that also a teacher who wants to teach it at a third grade level can get a job in the technical field. Right now, if we sort of mapped out onto something like mathematics, right, we'd say, well, yes, if you can, we're going to teach these courses in university to people who don't know any arithmetic or algebra. Well, that's remedial education. Right? And similarly, right, we don't expect that somebody who has a third grade math level of understanding, can teach third grade math is suddenly capable of doing technical work. It seems to me that there's some sort of weird disjunct in sort of what's hard and what's easy in computing, that we haven't successfully turned computing into something that separates out the sort of elementary stuff that you learn as part of your elementary education, but it's not considered, wow, you can get a job, from the stuff that is appropriate for teaching at a college level. So are we going to get there?
David, it's not the material, it's the economics of the situation. Those third grade teachers with a little knowledge of mathematics can go out and get computing jobs. It's just that they can't get mathematics jobs. When you look at what the Bureau of Labor Statistics says about the job growth in the STEM fields, it's all in computer science, but that's not where the degrees are being produced. There are 3 times as many job openings in computer science every year than there are degrees produced, and most of those degrees are coming from the for-profits. So, you probably don't want to count them. I mean, it's just not something. Just as a experiment, if you take the line item in the BLS current employment that's listed as mathematicians, and you list it's one level up. So I'm admitting that I'm the aggregate of all the computing professions. What's the ratio between the two? How many computer scientists are there for every person who's working as a mathematician? 1,000.
Yeah, I completely concur. Another interesting stat is you often hear in politicians talking about STEM jobs and how we need more STEM education to prepare more kids for these so-called STEM jobs. Most fields in STEM actually have unemployment. And I frequently speak to people, a parent whose child became a, mechanical engineer and is unemployed, or biologist and is unemployed. The word STEM jobs is accurate if you remove the STEM and replace it with computing. Something like 70% of all jobs across all STEM fields are for computing. Having said that, going back to the structure of your question, the teachers who learn how to teach AP computer science, in Java or whatever, those are the ones who really have learned enough coding that they can actually, leave their profession and become a programmer. The way the third grade curriculum is taught is actually hardly even involves the teacher. The teacher does get maybe 2 days of kind of learning how to run it, but it's almost entirely off the computer. And the Khan Academy has their version, and we have a slightly different. But essentially the way the Code.org curriculum works, first of all, it's maybe 1 hour a week. So it's, the third grade, the same third grade teacher teaches all the subjects, and 1 hour a week, maybe let's say at 10 o'clock on Thursdays is the Code.org hour. Everybody sits in front of their individual terminal, logs into wherever they are from last week, and then they start doing the problems, which are on-screen problems. It'll say, drag and drop the blocks to write a program to make the, Angry Bird find the pig, or so on. And then if you don't understand, click here, and there will be a short video by a child teaching you how it works. Or it might be a video by, we have a number of celebrity type, we have Mark Zuckerberg teaching you how for loops work, or Bill Gates teaching you how if-then statements work. But it is all actually taught to you on the computer. The teacher's role, it could be to leave and have a cigarette, but if they're still in the classroom, the teacher's role is to kind of walk around and, oh, is anybody stuck? You're stuck? Well, Sally here can help you figure out how to do it. It's really minimal. Those are not the teachers getting jobs elsewhere, but it is actually, these kids are learning a ton from this. And hopefully the teachers actually are also learning it and helping them, but they don't need to. It is possible to teach millions of kids these basics without waiting for all of those 3rd, 4th, 5th grade teachers to know them.
I think Lynn and Jonathan? Or?
Oh. I was going to suggest one thing along that continuum as well. So we at Minerva actually take a very strong stance that we don't teach introductory classes because that information is all available on the web, so why should we take students' money to teach that? It puts a lot of onus on the student, and I'm sure for some it's a very controversial stance, and like CS50, for example, is like the largest enrolled class at Harvard, so clearly there's some demand for it by the time students get here. But it is an interesting question over time of like, what is the role of computer science at a college, at university level, versus what do we expect students to come in knowing, either because it's just baked into the curriculum or because they are able to learn it. And then that affects whether or not you need the 1 to 600 lecture freshman year, or do you literally do that ahead of time and it's done over the course of their high school. And I think that's something that's going to be very interesting that plays out over next several years.
Actually, sorry, go ahead. I just actually wanted to pose a question, sorry, to Eric, which is, I wonder, maybe I'll, by the time I finish the sentence, I'll realize that it's a stupid question, but I wonder if the percentage of kids studying AP Computer Science A in high school went up, if enough, let's say if instead of 3% it was 85%, would that take enough pressure off your introductory class to kind of help some, would that make the problem worse or better?
I think the jury is out on that one. We'd have to see. We do not give credit for the AP, even the CSA, unless people take a follow-on course because we don't know what's in that class. So we use it for placement, and if you place out, then in fact you get the credit for it. But we found that to be the only workable strategy. And until we know a little bit more about how that's going, and the numbers in CSA are skyrocketing, as you know, along with CS principals because of the demand for CS. But there's still a lot that we find that people don't know when they come in, and we need to fix that before they can be successful.
So I'd like to actually take this question and step back a little bit, because I think the question of how we teach computer science, what computer science is, what people need to know, whether it's 3rd grade material or undergraduate material or highly technical graduate material, the answer is yes, it's all of those, and there's a lot of really exciting work going on to figure out which pieces are best shaped where. But this is actually not a panel solely about computer science or computer science education. We're here because of Harry and because of computer science education at Harvard. And one of the things that I believe really, really deeply is that computer science, or computing, computational thinking, if you will, is becoming like writing. It's a basic literacy skill that everybody needs. It's also a thing that some people need a different level of expertise in, and thank God for people like Guy Steele, but I'm not sure that that's what our 3rd graders need to know. But here at Harvard, and and certainly with Harry's guidance, computer science is a thing that is both an area you can dive into deeply and a thing that is connected. So I don't know whether you know this, Harry, but the reason I became a computer science major is I actually applied for a special concentration. I had this wonderful idea for a major that was going to encompass everything. And I wrote a brilliant proposal. And the very nice person who ran special concentrations at the time very nicely told me I was not going to be allowed to do a special concentration, but maybe I should try this brand new major. I am a member of the first class who, as a sophomore, could declare computer science. And they sent me to computer science. Now, I've never quite understood what the person who told me that was thinking when she said computer science was basically what I wanted to do because I wanted this very broad encompassing major. But I have, from time to time, thought she was really prescient. Because I do think that computer science and computing is touching and transforming everything. And so however we go about teaching it, to third graders, to undergraduates, to people online, to people who are interested in how they can use this to get a job, to change their lives, we should not be teaching them about the mechanics of computation without teaching them how that relates to their lives and their worlds and all the other things they care about. And that is what I learned as a computer science major here.
So I think that's a great place to end the panel and have us move to lunch. I would like, and I hope all of you would like to thank the outstanding panel. Again, Lynn Stein, David Malin, Eric Roberts, Jonathan Katzman, Hannah Bloomberg, and Ali Partovi. Let's thank them all.
Okay, welcome back for, I guess this is now part 3 in our new normal Harvard time. So our next speaker actually did her undergraduate degree in folklore and mythology. Later came back and started taking computer science courses through Harvard Extension, I believe. Ultimately did get a PhD and is now teaching the teachers. So working at Harvard Extension School, teaching us how to do really innovative things in the classroom. So with that, let me introduce Rebecca Nessen.
So Harvard Extension School is in many ways the outsider school of Harvard. Unlike the other schools, we don't have our own faculty. Unlike the other schools, our courses are open enrollment. Unlike the other schools, we don't have a research mission, just a teaching mission. Unlike the other schools, the majority of our courses are offered online. And unlike the other schools, the majority of our courses are offered in the evening. We are the night school of Harvard, the Harvard of night schools. But to many, we're still just night school. So sometimes I wonder about myself after having spent basically a third of my life pursuing 3 different degrees from 3 different insider schools of Harvard. Why is it that I feel so comfortable in my work at the Harvard Extension School, so like an insider in the outsider school? And a few weeks ago, Harry Lewis unwittingly answered this question for me. I started teaching at the Harvard Extension School about 15 years ago, both on campus and online. And there were high points. For instance, teaching students how to make a persuasive argument, both local and distance, starting first with speech and then writing it. And there were entertaining points, like the day when I was teaching about the free software movement and Richard Stallman crashed my class. But there was also that feeling of disconnection and distance from students who were taking the classes online. And sometimes the frustration of those kind of occasional technology hiccups that would disrupt teaching or make me feel or look foolish. And so on balance, it was worth it to me to teach online, but I felt like it was kind of a lesser, paler experience to the what I would be able to give to my students if they were in the classroom in front of me. A few years into teaching, I had an experience that fundamentally altered my perspective. I taught all of my students 1 year in what was then a popular 3D virtual world called Second Life. And to participate in my class, students needed to create an avatar. They needed to go find clothes and dress themselves. They needed to pick a name. And then they needed to teleport or fly to the location of our virtual classroom to have a live text-based discussion section. And the typing was really slow. The avatars were completely goofy. Every once in a while, there would be an interloper who would try to do something like sell us glasses of virtual wine. But I realized that there were certain things that were better about this experience than what I could offer in my face-to-face classroom. For instance, some of the students reported feeling that they could talk about riskier ideas and opinions they had when we were discussing controversial subjects, because of the protection that was afforded to them by their avatars and their pseudonyms. Other students who rarely spoke up, if ever, in their face-to-face classes would participate actively in our text-based discussions because they could pre-compose what they had to say, and they didn't have to vie for airtime with more aggressive, talkative students. This technology was clunky. It was a disadvantage in many ways. But there were lots of examples of how it was positive. And I realized that teaching with technology wasn't just a way to reach students who couldn't otherwise be there in my classroom. It had the potential to improve the learning experience for all students. Listening to myself say that now, it sounds kind of trite, old, tired. We've all heard it at this point. But there's still many teachers who have yet to have that personal conversion experience that makes it real for them. And so with my team at Harvard Extension School, we work every day to try to help faculty and students achieve that experience in their classes at Harvard Extension School. We're a long way now, both in terms of technology and teaching methodologies, what we know about what works, from where we were when I was teaching in Second Life. And it's in large part been led by faculty innovators, many of whom are here in the computer science department. Henry Leitner has been a pioneer and ambassador for all of our efforts of online teaching. Margot and Stuart have been pushing the boundaries of what they can do in their face-to-face classrooms each semester that I've heard about what they're doing and sometimes minorly helped with. And at Extension, we've been focused on developing and adapting technologies that help faculty teach their classes in ways that are personal and interactive and flexible, in contrast to the overarching movement towards the massively scalable. And Harry Lewis's teaching has been an exemplar of this change over time. It was 2001, I think, when I took CS 121 from Professor Lewis. It was a key step on what was a very crooked academic path for me. And I just have to take you back a little bit further to set the stage about that. In the late August 1994, I stood in Harvard Yard looking at Matthews Hall, where I was about to be moving in just a couple of weeks. And I had walked through Harvard Yard every single day on my way home from school at Cambridge Ringen Latin High School, but I just hadn't really looked at it. I had not really looked at all of the people who were there in Harvard Yard. And I asked myself that question that many Harvard freshmen ask themselves: do I really belong here? On my freshman orientation camping trip, I met Peter. He was confidently knitting a sweater as he told me that he was going to audition for the Crocodillos and join the Hasty Pudding. My tall, sunny roommate from Fort Lauderdale, Lisa, knew that she was going to concentrate in ec and Romance languages. She was going to make the varsity crew team. She would be an investment banker, and then when she had kids, she was going to stop working. And I can tell you she did all of that except quitting working. I did not really know what I wanted to do. I took up knitting. I joined the crew team as a coxswain. Academically, it seems like I was actually kind of interested in the same types of things that Guy Steele was telling us about earlier. I signed up for ancient Greek. I took Philosophy 140, deductive logic. And not even knowing that applied math was something I should look at, I signed up for Math 25, an advanced class in multivariable calculus. Within a couple of months, I was in some trouble academically. Ancient Greek was a lot of work, and it was hard. And frankly, I was just unprepared for Math 25. And I ended up taking a serious left turn away from my original set of interests and into the weird and wonderful, but entirely not computational, folklore and mythology concentration. That summer, Harry Lewis became the dean of the college. And while I was casting about in search of direction and belonging, he embarked on a set of policy changes which were ambitious, principled, and probably above all, wildly unpopular. He abolished the upper-class housing choice program in favor of randomization to increase the diversity of the undergraduate residential experience. And none of the students liked this, except that quietly I did, because I had ended up a failed coxswain in the athletics-dominated Mather House surrounded by football players and rowers. I see a few compatriots out there. He cracked down on undergraduate drinking. He took on the issue of how the ad board should handle sexual assault. He raised the minimum standards for what it took to be in good academic standing at the college so that you would have an earlier warning if a student was getting into trouble. The op-eds in the Crimson attacked every policy. Hundreds of students came out in protest of the decisions. A gigantic image of his face hung in the dining hall next to an image of Stalin. At an Adams House dance that I attended. Yes, yes. And for me, I was 100% intimidated. But Dean Lewis took the criticism head on. He stuck to his principles. He stood by his policies. When I graduated, I was much more confident. I was happy, I was proud, but I still had no idea what I wanted to do. And I knew I didn't want to be a doctor. I did not want to be a management consultant. I didn't want to be an investment banker. So I went to law school. In law school, luckily, I took Jonathan Zittrain's life-changing Internet and Society course. And I learned that code was law in this internet age, and that it was up to me to decide, did I want to be one of the people who was making those laws or one of the people who was reacting to them? So in my third year of law school, I cross-registered into CS50, which was taught by Stuart Schieber that semester. And I spent many happy late nights in the Science Center basement coding and getting help from TFs in silly hats. And sometime around October, I showed up in Stuart's office hours, and I said, I love CS50. I want to leave law school and do a PhD in computer science. Channeling his inner Harry Lewis, he very kindly told me that I was completely nuts. But that summer, after I graduated and passed the bar exam, I called up Skadden Arps law firm, and I told them I would not be joining them in New York that fall. Instead, as a special student, I registered to take CS 121. So on the first day of class, I was really nervous. Smart, hardworking people had told me that this was the hardest class that they had taken at Harvard. And 3 years after graduating, I was still 100% intimidated by Dean Lewis. But the class was wonderful. I ended up feeling like now I was sitting in the place where I should have started at the beginning. I love the elegance of the ideas. I loved that feeling of suspense and doubt when I was looking at a theorem and I had no idea how I was going to prove it. I loved the collaborative problem-solving office hours in Locher Commons and the thoughtful policy on collaboration that encouraged us to work together to think about the problems, but then had us work individually to write up and explain our solutions. But probably most of all, I loved the automata and the grammar formalisms. that Professor Lewis would draw on his transparencies that he used to give his lectures. So 7 years later, Harry Lewis sat on my thesis committee when I defended my dissertation, which was advised by Stuart Schieber and was filled with grammar formalisms. Today, with CS20, Harry has magnified the best and most effective aspects of that course that I took in 2001. He uses pre-recorded lectures so that he can spend his class time interacting with students who are broken up into small groups for collaborative problem solving. His longtime TA, Deborah, is here somewhere, Deborah, does the same at the Extension School, live and online, and also using small groups. It's the kind of teaching, online teaching, and the teaching methodologies that I and my team are trying to encourage every day. And I'm very proud of what we do at the Extension School. And I believe that my team is capable of helping faculty to creatively use technology to improve their classes for all of their students. But it wasn't until a couple of weeks ago that Harry helped me understand why I personally feel so at home at the Extension School. I was sitting in on a meeting of the Harvard Extension School Faculty Council, and the topic under discussion was whether the age for students pursuing an undergraduate degree at Harvard Extension School should be raised. Harry has sat on this faculty council for many years, and he asked, who are the students who would be affected by this change? And our academic dean told him, it's a very small number of students, actually, but for the most part, these are students who could not successfully attend a residential full-time program like the college. They include competitive athletes, performers, deployed military personnel, youthful entrepreneurs who are pursuing their startup dreams, and people with disabilities who can't, for one reason or another, live residentially or pursue their studies full-time. And with a characteristically sharp and principled response, Harry said, these are the oddballs. Are we trying to say that there's no place for oddballs here at Harvard? And I realized that in my own way, with my crooked, all over the place academic path, I too felt like an oddball at Harvard. And here it was, Harvard Extension School, a place for all of the academically able oddballs of any age. And so from one oddball, talking to the many others here and elsewhere, I would like for all of us to celebrate that we have a place at Harry Lewis's Harvard.
Okay, let's see. Our next speaker is Cliff Young. Cliff was a graduate student when I first got here as a faculty, and so I like to think that when I hired Cliff to help me TF what was CS50 in my first time teaching a class of 300, that we basically got to learn how to teach together, and it was a real pleasure. So on that note, he's going to tell you about all the really cool things he's been doing for the last 3 years.
So I thought I'd start with a second order Harry story. I think if you're in this room, then Harry has touched your life in some way, and we're all here because we appreciate the systematic and thoughtful and caring ways in which he has touched us. But I actually have a second order Harry story. I'll talk in a sec about how he helped me with key decisions in my life, but he actually started influencing my life, it turns out, before I even met him by about a year. As a prospective senior, I visited Harvard as one of the possible colleges I might attend, and sort of was trying to get a sense for fit, right? Like, you spend 4 years at the school, it makes sense to figure out, like, does this place have my people? Are they all jerks? Like, what, reputations are high. Is it good to be in a city or bad in a city? And all these other sorts of considerations, aside from, the excellent academics and so forth. And my host lived in this sky tower with an awesome view of the river, and I think he had founded multiple businesses, and he showed me for the first time RoboHack, which I don't know if you play Diablo, but Diablo is based on Hack. And RoboHack was this AI program which basically ran around the little text-based dungeon and automatically learned how to train the dog and eat the food and win the game by itself. And that was the coolest thing. Plus he had a Mac with a modem, and he was clearly dialed into the big mainframe computers, and it was like So I saw this and thought, wow, I could be a senior, and like that might be my trajectory. This is awesome. I got to go to this school. My host was Marty Chavez. So you may be observing the direct first-order effects of Harry on your career and on your life, but I submit that the second and higher-order effects are much, much wider-ranging and really quite amazing. And maybe it's anticlimax after that introductory story. And thank you, Marty, for the serendipitous, like, oh my goodness, could this guy have been my host back then story? Harry helped me choose computer science my freshman year. I think as many Harvard students do, I came with huge ambitions. I was going to be a mathematician. And then I took Math 25 with David Karger, among other people, but also all those Putnam exam winners. And I thought I'd major in English, and I took Shakespeare from R.G. Garber, which was illuminating, but convinced me that I couldn't write to save my life. And I took philosophy with Harvey C. Mansfield, and maybe we'll just leave it at that. But I also, I programmed my home computer in high school, and as a sort of side hobby thing, I took CS11 from, I think, Henry Leitner. No, wait, I'm sorry, I took CS150 from Henry Leitner and from Tom Cheatham. I'll have to go back and look up who I took CS11 from. And so at the end of freshman year, one has to declare one's concentration. And I sort of thought about, like, do I want to be a physics person? Wait, I haven't taken any physics. And this math stuff, boy. And my roommate had taken CS121 and said, talk to Harry. He's the head tutor. I understand that title has been reassigned to now it's Director of Undergraduate Studies. But so I took Harry out to 3 Aces for lunch, and he told me, well, all these things you're interested in, Cliff, you can still do them inside of computer science, right? I've got this general purpose major, and you can specialize it however you'd like. So I'll come back to that theme in the talk. Harry also persuaded me to come back to Harvard for grad school, which is interesting because I think one of his undergraduate pieces of advice was don't go to grad school where you went to college. So that, happily for me, there was 3 years of working between college and grad school, and Harvard had changed between when I went off to college, when I graduated from college and when I was looking for a place to do a systems PhD. We had hired H.T. Kung, and H.T. promised that some awesome junior professors were on the way too. Those turned out to be Margot Seltzer and Mike Smith. So Mike advised me. So that was quite a home run and quite a set of excellent advice that has been life-shaping. So I'll come back to Harry in a minute. Let me, oh no, my computer's timed out. Let me give the nerdy part of the talk. So, hints for special purpose computer system design. We're in this room because of Moore's Law to some extent, although Moore's Law, I guess, is a coda to that Alan Turing guy. But at least during my lifetime, Moore's Law has been operating, right? Gordon Moore of Intel observes in 1965 that it looks like the transistor count on these integrated circuits is doubling every 18 months. And that's like been a self-fulfilling prophecy for all of my life. In fact, during the 90s, there was this miraculous period where that doubling every 18 months actually translated directly from transistor count into delivered performance. And so we had this era which corresponds with the second AI winter, which has been also renamed Attack of the Killer Micros. And so during that period, we started the 90s with like weird and varied supercomputers of various sorts and Lisp machines, and we ended it with Intel. But we ended it with Intel with staggering performance, right? Buy a desktop machine in that era, and it was just unbelievable what you could do on your desktop. My material science grad student roommate was doing his research simulations on his home PC when he wasn't playing games on it. There was kind of a surprise in 2006 when Intel introduced the so-called Core 2 Duo architecture. I've highlighted Duo. The 2 is just modifying Core. It's a second-generation Core architecture. But the Duo is there were 2 processors on 1 chip in that machine in 2006. And this is kind of a weird indication that Intel was throwing the towel in, that after years and years of the march of the killer micros and staggering uniprocessor performance gains, suddenly Intel, the manufacturer of reference of computing cycles on the planet, took a left turn and said, we're not doing this anymore. For your future machines, 2 and 4, and in the case of 18, cores into a single chip because we're out of ideas. We have taken all the beautiful ideas from 1960s supercomputing and stuck them on the chip, and now we got 2 of them. And it looks like there is more and more of those sorts of cores. And so, disappointingly, for the last decade, you buy the new machine and it doesn't. Sorry, I can't help with that. But it gets worse. And so most of my professional career, I've heard people say Moore's law is close to its end. I got to Bell Labs in '97 and people said, we're pretty close to 5 atoms of insulator, and you can't build a transistor without insulator. That was, what, 20 years ago? So we're still building transistors. They found ways around some of those, but ITRS, the industrial forum that was doing the self-fulfilling prophecy business, gave up a few years ago. And Intel itself is advising that Moore's law is slowing down. So when Intel itself is telling you that this is happening, you should believe it. The transistor game is about to become zero-sum. You buy this much area, you get this many transistors, and it's not going to get better. So one question is, what should we do next? And the answer that I've been exploring for about 15 years of my career is special purpose computing. And I say return to special purpose computing because, as we know from the Aiken Mark I and from the cryptographic work during World War II, computers started special purpose in cryptography, ballistics, and maybe plasma simulation. They became general, but now it may be that we'll turn things back and make them specialized again. So what do I mean by special purpose computer, or equivalently, the new hot term is domain-specific architecture. That has somewhat of a more nice ring to it. A computing system designed to perform well on a limited set of tasks. So DSPs you know about, graphics processing units are actually surprisingly general these days. Any embedded device, right? It's, you know, by doodads around my home have computers in them these days, and so they're specialized in certain ways. And the coming Internet of Things, which is going to be either wonderful or terrible or both. My personal experiences are in molecular dynamics and machine learning. I spent 10 years at a place called D.E. Shaw Research building Anton supercomputers. Those are perhaps more known in the academic HPC world, but our goal starting in 2003 was to build a 1,000x faster machine than National Labs supercomputers of 2003. And we succeeded in a 5-year effort. And so in 2008, the first machine came up and was only 100 times faster than the existing National Labs machines, but that was part of the plan, because we knew about Moore's law, and the goal was to steal a march on Moore's law, aim for 1,000, take 5 years to get there, end up with 100. I'll come back to that in a sec. The last 4 years, I've been at Google building the tensor processing unit, which is special purpose hardware that Google is deploying to do deep learning. And so deep learning is the new hotness in the valley, and in tech, it's the basis of this third wave of AI. Delightfully, it actually works. And so aside from recognizing cats, we are improving search ranking and recognizing speech and playing the game of Go at superhuman accuracy and translating human languages to other human languages better than we were ever able to do before with machine learning systems. Uh-oh. Oh no, sorry. And now I'm showing you the pages. Oh, there we go. Okay. Right. So special purpose computing, and I lost my train of thought. Next slide. Okay. Right. Playing the game of Go and translating human languages, which is kind of cool. And I think it's so far at this point in this wave of the AI revolution, we keep on finding new applications, and that's awfully cool too. We haven't started to see the limits of that. So. When people hear special purpose computer, that's subject to a little bit of misinterpretation. That doesn't mean a computer that does just the one thing. It's not that somebody published a paper on a particular neural network and we baked that one neural network to recognize cats into the hardware. In fact, you can pull back a little bit from that and build one computer that both recognizes cats and processes speech and plays Go. And another fallacy which goes in hand with that is that special purpose computers are not programmable. In fact, they're computers. You got a chip. You can put the transistors on it however you'd like. If you'd like an instruction sequencer on it, if you'd like to have it have an instruction set, you can totally do that. You can also build it to be a widget that just takes bits in on one side and spits bits out on the other side, but you have the entire playing field to work in. And so a better way to think about it is if there's picking a point in a spectrum with Intel CPUs on one end, incredibly general, incredibly high value, does everything, completely fixed function at the other end. And what you want to do is choose a point in that spectrum that has the right balance of specialization and high performance on your application area and the right amount of programmability so you have some room to work. And maybe a better way still is to talk about searching a multidimensional design space. So you've got all these engineering constraints of cost, performance, energy, functionality, programmability. Which point do you pick in that multidimensional space to deliver the best value for your users? So the talk that I proposed to Margot is titled Hints for Special Purpose Computer System Design. This is homage or stolen from a classic paper from far too many years ago by Butler Lamson, which was titled Hints for Computer System Design. Butler wrote it for SOSP 9 just after the foundational work at Xerox PARC inventing the computer systems that we use every day today. And was, I guess, we work in a non-modular field. Like, systems are messy and not necessarily all that theoretically factorable or clean. But it turns out that I think the hint-based approach that Butler took is a very effective way to capture knowledge and try to think systematically, or at least point out dimensions of tension or difficulty in solving these system problems that are kind of interesting. Butler's paper has this hilarious list of caveats, which I won't read out loud, but I think it's also interesting that the paper incorporates quotes from from Hamlet, where Polonius is giving advice to Hamlet, and Polonius is, the terrible uncle who lectures you with all the boring examples of things you don't actually care about. And so I think Butler reached a wonderful level of self-deprecation in quoting Polonius. I'm not going to be quite that erudite in this talk, but I think the point of the caveats and the Polonius quotes is not guaranteed to work, but still interesting. Okay, so I think I have 3 areas of hints: scope, methods, and delivery. Scope is, where do you draw your line around the problem? Methods is, the reason you're specializing is to get performance on these things. So how might one think about performance? What are things that might be broadly applicable to that? And delivery, one of the papers I enjoyed writing about the Anton machines had a line saying, history is littered with the corpses of special purpose machines. That remains true. And so how do you not end up one of the corpses, or roadkill, in this process? So scope. 3 hints here. Spend time with the chemists. Algorithms are at least as important as architecture, and choose your system boundary. Spend time with the chemists. So you're working for a particular application. You're not building a general purpose machine. You have application experts to work with. They have their own methods, results, and hunches. So, this is the core curriculum mandate, right? Let's go familiarize ourselves with the approaches to knowledge from this nearby field. Find common ground and common language. So with the computational chemists, they are computational chemists. They know how to hack, and they know how to hack on supercomputers. They don't necessarily know about pipelining and out of order, but you can teach them. And they, in turn, might teach you about symplectic integrators, or they might teach you about quantum physics and so forth. And by co-designing, by each of you learning a little bit about each other's field, which goes back to Harry's general purpose major, and you can go specialize in whatever you want. But by doing that kind of co-design, you can actually do better than either of you would have done in isolation. Let's see. I actually jumped to my 3rd point. But my 2nd point, it takes a long time to build these machines. So you're not actually building the machine for what they're doing now. You're building the machine for what they're going to want to be doing in 2 or 3 years. So how do you guess about where the machine's going to be in 2 or 3 years? You got to predict the future, which is, of course, impossible. Even the finance guys have some trouble with this. So there is, however, a good forecast in your colleagues' heads, because they're the people doing the research, right? They have their hunches. They won't necessarily prove it out. They don't know for sure, but they sort of think this area is going to be hot. This technique, while it's not working now, might be working, or a relative of it might be working in 3 years. And so by listening to them about what they're doing now and what their hunches are, you can actually meet the problem where it's going to be. I added a caveat here. That's a positive statement. What do you think might happen? Don't at all believe them when they say, oh, I don't need this. So one of the TPU stories is in the spirit of going fast, we created a list of stuff we were definitely not going to do in the first TPU. And we had all our clients sign off on that list. Totally won't do this feature, won't do that feature, won't do that feature. And we happily went and built our machines. And about 6 months into, the bullets launched, the machine's out for fabrication, research breakthrough, the new inception method comes back for recognizing cats better than before, and they blew 5 of our assumptions, right? So I spent like a year building hacky software workarounds to try to map the 5 broken assumptions back onto the device. So take that with a grain of salt. Anyway, back to the co-design problem. You have your set of constraints in hardware and software. They have their set of constraints in terms of the math or the physics or the algorithms that they care about. Some things are don't cares. And so rather than the terrible trade-off business of I win, you lose, zero-sum engineering, you can often find spaces at the intersections of fields where 2 don't cares, or a don't care plus a care on the other side turns into a much better solution than you might have otherwise chosen. Algorithms matter at least as much as hardware. My model checking friends say that during a 15-year period, they got 1,000x from the hardware and 1,000x from algorithmic advances. There are asymptotic differences in some of the parallelizations in the Anton machines, where an n-cubed algorithm became an n to the 1.5 communication load, which meant we could double down on compute instead of communication. And there are restatements. So there's this, if you're in material science, you might have hit the Ewald sum. It turns out that the classic statement of that uses splines, which are not radially symmetric. Our chemists came up with a formulation of that was radially symmetric in 3-space, and by having a radially symmetric formulation of that calculation, we could take two previously separated hardware systems, fuse them into a single one, and save that space and design time, better solution overall, zero cost, aside from having noticed the overlap. One caveat about the algorithms, though, is that they really have no loyalty to your hardware. So we invented a number of new algorithms for the Anton machines, and then as part of our internal development efforts, we also had the competing software on a supercomputer cluster effort. And we ported a bunch of the algorithms that we built for the beautiful hardware back to the cluster code. And so my 100x target actually turned into 30x, where our own worst competitor was our internal software package. And so you might have the great methods, but don't expect them just to stick to your beautiful hardware system. They might just walk somewhere else. Okay, and choose your system boundary. Pick the problem you work on. So one pitfall in this space is you profile your current program and you see that 90% of the time goes to one thing. And you might have an incredibly beautiful algorithm for doing that one thing, like matrix multiplication or Fourier transforms and so forth, and spend all your time there. And I'm here to tell you, if you want a gigantic speed up on your machine, you probably shouldn't focus all on that, because there's still the leftover rest of your program that might come and get you, right? That if you have a 90% profile item and you make its time become 0, Amdahl's law says that your maximum speed up is 10x. So everything else suddenly starts dominating where you spend your time. A bunch of this is just choose the proper problem. Where's the boundary of the system? If you look at early general purpose GPUs, a bunch of them don't deliver performance because there's all these back and forths between the host machine and the GPU accelerator. There's an inflection point in 2005 or so where people start pushing stuff off the CPUs onto the GPUs entirely, and then by removing that communication bottleneck, they get these incredible 10x and sometimes 100x speedups. And both Anton systems and TPUs have that. They incorporate the entire problem on device so that you don't have to go talk to the rest of the world to solve your problem. And then the domain of acceleration is entirely covered by what you're controlling, rather than having to, again, talk over slow, only 100 gigabit buses back to host CPUs. Okay, so that was scope hints. My middle section is methodology hints about Amdahl's law, about being sure to learn the math and not being philosophically inflexible. So Amdahl's law is the thing I said before. If you take your 90% item and make it 0, your max speedup is 10, right? So in software land, this means work on the first and second things and don't bother with the rest, because when you're done with the first thing, you've taken your 90% item and you've heroically optimized it, and it's now 30%. And that means it's still 3 times longer than your second item. So it doesn't actually matter what the second software item to speed up is. Hardware breaks this, right? You take the top profile item, you take your 90% and you make it 0, right, by heroic design efforts. Then you take your 9% item. And that wasn't worth optimizing before because it was too small. And it wasn't worth optimizing in software land, but in hardware land, now it's 9% of the remainder. Sorry, it's 9% of the 10%, so it's really 90% again. So why don't you kill that? And while you're at it, you could throw in more hardware so that both the first and second things operate on independent pieces of hardware, so that all of this becomes parallel. So you can actually iterate in your application of Amdahl's law bottleneck removal. At some point, you'll end up optimizing crazy things. So I was staring at molecular dynamics code for bond terms, which is 0.1% of the original profile. But if you want to build a 1000x machine, you better be tuning stuff that was 0.1% of the original profile. Otherwise, you haven't killed enough stuff off. Optimize the crazy things, and then keep on going. So maybe a quick way of stating this is be aware of where the speed of light is in your design, what the fundamental constraints of the hardware are, what the fundamental constraints of the algorithm are, and think about how you can violate them. Second thing in methods, learn enough of the math. I worry a little bit that we're suffering from another 2 cultures evolution between computer science and the applied sciences that we are so closely coupled to, that partially as a result of Math 25, I ran screaming away from continuous mathematics and managed to avoid it for the rest of my undergraduate career. The math courses I took were even discrete. But the application domains are physics and mathematics and deep learning, and they want real numbers, and they want continuity, and they want differentiation. So you should be careful to actually learn those things, because you got to implement them. The fields actually cross over in computer arithmetic, which we didn't have that much of when I was an undergraduate. But basically, you can fake continuous quantities using 32 and 64-bit quantities if you're careful. And then there's all sorts of devils in the details inside of that. There are incredibly powerful algorithms in this space which have beautiful scaling and dangerous numerical properties. So matrix multiplication is an n-cubed compute algorithm with an n-squared I/O characteristic to it. And that's part of the power of TPUs, that they are great matrix multiplication machines. The fast Fourier transform, which is an n log n algorithm that is a replacement for an n-squared algorithm, also turns out to be more numerically accurate, which you don't see in any introduction to the FFT, because who cares about numerical accuracy in this field? But you might care about that, depending on what quality results you want. And maybe this is an old one, but because float is not actually associative, even though reals are associative, float is not associative, summation can cause you a world of problems, and so watch out for that. Anyway, learn the math. Learn the math that your domain scientists actually care about, which is a specialized subset of the math. And again, look for the ways in which you can do co-design. Third part in this section is don't be doctrinaire or know the history. And so there's this temptation in both academia and industry to fight religious wars. Like, I've got the best thing. This is the answer to the problems of this field. Like functional programming languages. Remember those? They're still here, right? Imperative programming languages. The RISC-CISC debate. The SIMD-MIMD wars in parallelism in the 80s. Should you do things statically or dynamically in instruction scheduling? And data flow is the answer to all of these problems. And I've participated in these wars. I'm the author of a book on VLIW. Yay, we could talk about that offline over a beer. The truth is that each of these techniques are, again, trade-offs. They come up with a set of strengths and weaknesses. And depending on the situation, different techniques are a better match. So for the programmable parts of Anton machines, I built VLIW, SIMD, multiply, accumulate, multi-core, multi-chip solutions, but not multi-threaded because that wasn't actually a match for the problem. We didn't need throughput, which multi-threading helps with, so we didn't do that. And for the TPU, we have a CISC instruction set. Who builds a CISC instruction set in 2013? I do. And we build systolic array multiplication units, which I'm sorry HT isn't here, but his glorious idea from 1973 or so, where the hardware they could fabricate back when I was a graduate student was sort of 8 ALUs hooked together by a high-performance network on separate chips. We have 64K arithmetic logical units on the current TPU. So the technology has enabled an architectural idea which was difficult to prove 30 years ago to be just drop it into the chip. In fact, make it into the big hammer. That's actually the source of competitive advantage. So another way of saying this might tie back to the educational thread that many other majors had sophomore and freshman seminars. For a long time, computer science hasn't. I think Harry's about to found one with his 50 computer science papers that everybody should read. But we expect our artists and their critics, our humanists, to know the histories of their fields. We expect the artists to actually be able to practice each of the previous styles in their fields before they go on to innovate at the edge of creation. So what's with system architects? You really ought to know about these systolic bits of history because they might actually be the right answer. Okay, last section of hints are about delivery. I think these should be faster. So buy insurance. You're dedicating your silicon to do a bunch of stuff. There's a core part of your application. You must do that. There's a bunch of stuff that your researchers have told you might happen, right? Those are might do, depending on where the field goes. You should view those as insurance policies against the field shifting, that your machine will remain viable even if this change in the fundamental algorithms happens. So think about it in terms of insurance. What's the upfront cost versus the deductible, right? The upfront cost is hardware design and verification. The deductible is building the software stack out to actually implement that feature in production. And in fact, you should manage this like an insurance portfolio, right? There's a bunch of different things you want to insure against. How much are they going to cost you in aggregate? How much might you pay for them in the end? If you put these in, you should expect that some of them won't be used. And that's not a failure, that's actually a win. You want to not exercise all of your insurance. In fact, if you used all the features, you underinsured. Manage risks explicitly. This is in some ways obvious, but there's a temptation in these aggressive projects to reach for all this super duper technology. Like, let's go gallium arsenide, or let's go super duper latest signaling speed at 56 gigahertz or 112 gigahertz or whatnot. Each of those introduces risk of failure into your project. Are they must-do kinds of things? Like if you take 3 80% likely to succeed technologies that put them into your project, and they're independent, then your likelihood of the whole project succeeding is 50%. That's a lot to spend $50 million on. So, maybe you should be very, very careful about these risk tokens and what they weigh. What's your bailout when this particular piece of the technology fails? And I suppose bitter experience says, especially watch out for that nasty analog stuff, because that always seems to be the problem. That like DRAM is analog, horrible capacitors inside of like these tiny little structures that are far too tall and skinny. Host buses are also actually terrible analog sorts of stuff, and interchip interconnects at high-speed signaling rates of 56 gigahertz are also horrible analog stuff with oscilloscopes. And that, those of us who like discrete mathematics and beautiful bits and so forth don't like to think about that, but it's all just underneath the surface ready to come and bite us. Okay, and the last section of these sort of Polonius-like bits of advice is programmability is hard. And let me draw a distinction here between flexibility and programmability in your weird machines, or maybe in general. So I define flexibility as the hardware can do it, right? In conjunction with a hero programmer who already knows the architecture super well, of which there are 3 on the planet. And programmability is the average Java programmer can do it. There's a huge gap between flexibility and programmability. And I think a perfectly reasonable user request is, can I have both your teraflops of performance and programmability at the same time? And in fact, this is perhaps the hardest dimension of engineering. I don't have a magic bullet for programmability versus flexibility. In fact, I think maybe the right answer is to say, make sure your users understand how hard it's going to be to program the machine. Because even though you might have put some stuff in to make things more modular or more clean, or to use the right syntax in the language that you program the machine with, you might still have a massively parallel machine with a weird functional unit on it that uses a numerical representation that nobody is familiar with. And so there's still 3 degrees of difficulty, even though they're not programming in assembly. Okay, so altogether, 3 major areas for hints: scope, methods, and delivery. I probably shouldn't read them all back to you once again. I was looking for a way to tie this back to Harry, though, and I was thinking about sort of generality and special purposeness, and how, for many of us coming to Harvard, the reason to come to Harvard was the liberal arts education and the possibility that it was a university that all subjects under the sun could equally be studied here. In some sense, some of our roommates knew what they were doing, like from birth, but many of us came in some sort of protean, unformed state. We were generalists when we got here, and part of the path was testing what our strengths were and what was hard and what was easy, and you can only do that through experience, right? And so I view part of my Harvard experience as a choice about specialization. I chose to specialize in computer science, and I chose to do systems, and later I chose to focus in on compilers and computer architecture, and sort of making these kinds of trade-offs in my personal life that are very similar to these sorts of design trade-offs that one makes in building a special purpose computer. Weigh the risks, think about what the return are, have a portfolio of investments. So I think Harry has been singular in pointing out, oh, you have this flexibility, Cliff. Why don't you try this out? Why don't you go work with this person in similar sorts of ways that are akin to spending time with the chemists and understanding what the history is. So let me wrap up by saying, a couple years ago, I came for my 25th reunion, and that was an amazing experience that you might say was horizontally biased in time, that the sample of people that 25 years ago all met in the yard, or 29 years ago all met in the yard, came back together and exchanged stories. And we had the Math 25 reunion photo and so forth. And that was a wonderful view of some part of my Harvard experience. This get-together is a vertical view. And I'm just amazed. I think I actually got 2 different decades of Harry. So the 80s decade of Harry and the 90s decade of Harry. But it's been a delight to re-encounter friends and renew acquaintances, and also to hear about the eras that came before and after. And I am amazed at the range of your impact and the breadth of your vision, Harry. Thank you for being such a wonderful influence on my life and on all of us in the room.
Okay, our next speaker wins the I Came the Farthest to Be Here award. Arrived last night on a long flight from Berlin. And so there he is. Christoph Freitag is going to talk to us about travels east and west.
Okay. Yeah, I would like to shift a little bit from the technical part to a little bit more the personal part. And we have heard already many things about Harry, and I want to add a few things. And since we also talked about teaching, and everybody sits so comfortably here, I want to get you out of this mode, especially Harry. So I will give you at least 3 questions today, and you have to answer. And if you don't answer, you can think about what I will get, okay? This is interaction, isn't it? So we should not only preach it, but we should also teach it, okay? So why did I call it Going East and Going West? As Margot already said, I'm this weird guy coming from Berlin, and almost 38 years ago, I came from Hamburg, and I want to tie my experience with Harry to the different events I had with him. And to be honest, it took some time to get to know Harry, and I can't say that I got to know him during my time here at Harvard. It was only later, when you visited me in Berlin, that we really had a chance to open up and exchange certain things and learn about each other. Okay. So, for those of you who don't know where I am from, let me see. Oh boy, now I have to get the right button again. Berlin is not in the center of Germany, but it's actually towards the Polish border, okay? And that's where I have been over the last 23 years. I was actually born in Berlin, actually on the wrong side of the wall in East Berlin. My father was a PhD student in physics at the university where I now teach, namely at Humboldt University, which is one of the 3 universities in Berlin. And it was actually in the east side. This is the main building. It is actually a palace of a Prussian princess, and the university was founded in 1810. The building didn't look like this about 30 years ago. Actually, I have to bring you back to reality by looking at this picture, namely the year that I joined Harvard in 1979. This was the picture in Berlin, namely the Brandenburg Gate, separating West Berlin on the left from East Berlin to the right. And for me, I spent the first 8 years of my life in East Berlin until my parents made the decision to jump the wall, actually 13 months after the wall came up. And that gave me the opportunity to come to Harvard. Otherwise, I would have stayed in East Germany and probably wouldn't have been able to go to university because my father was a educated person, and due to the communist system, I would have learned probably a blue-collar job, okay? So this was already the first chance I had. And so my parents settled in Hamburg, and that was the starting point for coming to Harvard. And I really didn't know what I was getting into. Harvard was a name for me, an excellent university, but I had no idea. I was almost a failing student in Hamburg. So my father kicked my back and said, you have to do something different. And I applied for a scholarship. I got it. And I showed up at Harvard, and the first person I met was Harry, who told me, well, you have to take certain classes. And one of the classes was, of course, his own, namely A108. And I felt miserable because I was not very good in theory. But after this one semester, what I'd learned is that theory can really be fun. Learning about this pigeonhole principle and other nice things. And actually, we heard already today that was the time when his book was slowly getting into shape. So actually, after this one semester, I really felt theory can be fun. And it actually has turned out that theory has always been part of my career, even though I never got into theory per se, but I always say the best systems person is one who knows a lot about theory. And I think that's what I also tell my students, since I'm a teacher myself at Humboldt University. That's what I usually also tell them. So you have been a very inspiring teacher. And you have to apologize. We are now in the digital age, but I couldn't find any picture of the time when we first met from 1979. Even on your webpage, nothing's there. You are only shown in this from probably 2001 and younger. Okay, so now comes the first question. I came as somebody from Germany, and nobody really knew. I didn't expect, and until today, I asked myself, why was I accepted at Harvard? And I never asked this question to Harry. I came with a scholarship. Probably they felt he comes for 1 year, and if he's not good enough, he will disappear again. And if he's good enough, well, what happens then? So one person actually gave me an answer to that, and that was an almost finishing student. And I want to know who this guy is. Do you remember, Harry? I give you a hint. He was Tom Chetham's student. He was actually also German, and he told me, you have to be very careful at Harvard because Germans usually have a very good reputation. The bar is much higher than for many other students. Erhard Plödereder. Very good, very good. So he is now a professor at Stuttgart, and he actually was an outgoing student just finishing his PhD, and he actually told me, be aware from German students, they always expect more than from any other students. So I didn't know what to make out of it, okay? So lucky Harry, okay. Okay. So then after I finished my master's time, and as a good German student, rather than staying here, I had the offer from Phil Bernstein. I said, as a good German student, first of all, let me go back to Germany and finish my study there. And 2 years later, Harry wrote a nice recommendation letter, and Phil Bernstein did, and I came back because I wanted to get into database systems. And so I had 2 teaching fellowships during the 3 years I was here, one with Harry, AS11, that was an experience with the head TA sitting also here, John Ramsdell. And then I was also able to be a teaching fellow together with Bill Gazarj, in a course with Michael Rabin. I mean, that was also putting me now at the seat of being a teacher was something different than listening to a theory. Okay. Now I tell you a story, Harry, probably you are not aware of it, but with AS11, since John was the head TA, at the end of the semester, we had to prepare all these grade sheets, and you asked John to show up on a Sunday morning at 10 o'clock, and he asked me to help him to finish the final sheets. And then I think it was around midnight we were done, and then we went dancing, and around 4 o'clock we came back to Aiken, and I fell asleep. And when I woke up, it was around noon. The meeting had already taken place. You probably didn't know. He knew, and I was totally embarrassed. And I asked him what happened, and he said Harry didn't care. So I wasn't sure what to make out of it. But that was one of the few experiences that I had. But it was somehow telling something about you. You wanted to get things done. You were very easygoing. On the other hand, you also had your expectations, and that was good about it. This picture is famous. So, name all the people on this picture, please. Okay. We start from the left. Okay, next.
Who was the ringleader in organizing this?
We'll tell you later.
So that's Christoph?
Yes.
And then that is Anders Weinstein, right? Yep. And then Craig Partridge behind them. Then over is Lisa Hellerstein, who's a professor at NYU. And that's Penny Chase, who is still at MITRE. Michael Massimilla in the foreground, who's here right now somewhere.
Is he?
Yeah.
Ah, interesting. Okay, I didn't recognize it. Okay.
Is that John Thielens directly behind?
No.
That's Thielens is all the way in the back. Thielens, you can just see my hair. Yeah, this is all the way in the back, right? Barely. So that's Phil Stern. Yep. That's Phil Stern. Who's here, right? And then the next person over to the right is Larry Lebowitz, who's here.
Yes.
And then is that Michael Cote in the back? Yep. Yes. Who's passed away. Then hiding behind Larry is Phil Klein, who's a CS professor at Brown. And to his right is Ronnie Seebach, who's at One Beyond. And there's John Ramsdell in the back. Beth Adelson is the next one in front. That's Jonathan Amsterdam in the bottom right. And is that Ted Nessett?
You made it. Congratulations. You are now close to a certificate that you can teach another 10 years, okay? So, I know, yes. I also don't want to hide the turbulent times I got into. I mean, we already heard about some of the lows. For me, the low was when Phil Bernstein left Harvard. That was in the spring of '83. Phil, for those who don't know, was in database systems. He got denied tenure. I was his student coming the year before, and I felt without a home. And so I had to decide what to do. And what did I do? I went to Harry. And I was probably like a rocket. I can't remember anymore. I was probably not very polite to you and asked all these questions, why did this happen and so on. And Harry was very calm and said, we'll get it done, we'll make it happen. And indeed, he succeeded in getting me through these last 2.5 years with still providing the financial support, still having an environment where I could grow and where I could do my thesis. And so I'm very thankful for him that he didn't let me down, but really got me through this very difficult time. I don't know how you experienced that time. It probably was not always very comfortable for you. So we made it. The only thing I remember is I think it was the dean. I had a bet with him that until the following fall, they wouldn't have a substitute for Phil, and they didn't have. So what I got out of this was a very nice dinner at one of the best fish restaurants in Boston. Okay. The other problem was I wasn't as fast as I wanted to be with getting my thesis done. So by the spring, I hadn't written one page. So it was time to speed up. And I think at the beginning of June, I ran out of money. And again, what should I do? And I went to Harry and said, well, Harry, I need at least another 3 or 4 months of financial support. And Harry, without stopping, said, we'll make it happen. And it happened. So by the fall of '85, I had a written thesis and I could defend it. The defense was also a big experience for me because all the faculty members showed up. And I felt very, very tiny because everybody seemed to know what I was about to say about my thesis, which I worked hard on for 3 years. But fortunately, I succeeded to finish. And then I got my dream job because this being here opened many, many doors, and I was never aware of it. So I went to IBM Almaden Research Center, to the Mecca for database systems, reading before all the names on the papers and now being part of it. That was really my dream job. Unfortunately, I only spent there 2 years. My wife wanted to go back to Germany. I followed her advice. We went back. We lived for 9 years in Munich. I had 2 different jobs in industrial research. One again with digital equipment, a company that doesn't exist anymore. I got this job through Phil Bernstein, who at that time was already had joined Microsoft, starting a small research lab. But then digital went down the drain, and it was also a very painful experience for me. I had a small group of 5 people working with me or for me. I had to let them go, and I had to find a job. And you have to remember, and that is my next question, the wall came down. When did the wall actually came down? Sorry, European history. Should I open up? 1989. What did you say? Okay, 1989. Do you know the exact date? Pardon? November 9th, yeah. If you are very good in German history, November 8th, November 9th is a very historical day on various years. There are at least 3 different events that happened over the last 130 years. Not very good ones in German history, but all happened on November 8th, November 9th. So this one is the happiest one. And while I watched the wall go up, because we lived about 200 meters away from the border between East and West Berlin, this time I could only watch it on TV. As I said, in 1994, we moved from Munich to Berlin. And for me, it was also a very interesting experience seeing 2 different countries melting together, speaking the same language, but having different social backgrounds. So that was a very interesting experience because many of my workers at the universities came from East Germany, and I felt pretty good, well equipped to do this, okay? So coming back to you, you are an incredible supporter. I always valued that you were able to get me through these difficult times and getting me to my PhD, which opened many doors. I also want to remind you of that book, because that book really helped me not only to learn a lot about theory, but I still recommend this book to my students because it's, I think, not only content-wise, but also as it is presented, very precise, very modular, and so I really feel that you should, I think there's out a second version of the book, but you should make sure that it is not forgotten. Yeah? So I still give it to students, and I have to make sure that they get it back to me because you can't buy it anymore. The third time was in 2008. I was on sabbatical, and so I thought maybe I should come back to Harvard. There was already a new database professor, so where should I stay? Harry had this great idea. He had this friend at Eliot House, the master, you remember, and he got me the Matheson room. I don't know if you know this room. It is a historic room. It's actually a library with 1,500 plus books around you, and had my little desk, my little bed in there. It was an incredible environment. I lived together with these undergraduates. I got to know to them. I got to know to the master. I felt like in a large family, and it was only due to Harry that I was able to get this assignment, and I really enjoyed the time here, besides also having a good time on the academic side. So, creative host, okay? So that was me going always from east to west and further west to California and going back east to Munich and then to Berlin. So then, and I also don't want to forget, during that time I also got to know your two books, and I know that there are some more, but they really also showed me that you think about other aspects as well, very deeply. And the Excellence Without Soul gave me a different view of Harvard with all of its pros and cons, and I started to read it a second time right now. And the other one I also found very inspiring because you explain computer science to an average Joe and not to the specialists that we are all around in this room, okay? So I think it's also very important that we as computer scientists try to give an understanding of our field to other people as well. Yeah, and then it was time for Harry to go east, yes. Namely, he visited Berlin in May 2013, and my next question is, what was the actual reason why you came to Europe? Yes, actually in Amsterdam, if I remember correctly, or was it in Düsseldorf? It was in Düsseldorf, okay. So he made the side trip, and I couldn't resist to convince him. So he gave also a talk on flipping the classroom, which was well attended. We actually also had him, he gave a talk at the Harvard Club in Berlin, which was also well received. And as you can see, there are not only two, but three people on this, and this was a longtime friend. Who was my classmate at Roxbury Lab. Okay, so he came from southern Germany, so we had a good time, and Harry probably needed one pair of walking shoes because we all walked around for many, many hours in Berlin, and I'm trying to show him both sides, East and West Berlin. It has been rebuilt, so there are many places from museums, which we didn't go into, going down unter den Linden, passing at many places. Do you remember what this building is? You actually nicely describe it in your blog, and if you want to know more about it, it is called the Kommode. It is the Humboldt Law School, more or less, and the interesting part is in front of this building, again, part of bad German history, that was the plaza where all the books of Jewish authors were burned under the Nazis. And if you go there there is a very nice memorial on that, unfortunately, bad event. Do you remember what this memorial looked like? It is an empty library, which you can look from the top down into the basement in the middle of this plaza. And I think it's a very appropriate way to remember this event. So during that time, we had many, many hours of talking, sitting around, enjoying the sun, as you can see, and I really got to know you as a warm-hearted friend with many, many aspects that I probably missed while I was at Harvard, because I was this graduate student and you was this wise and professor, and I only later realized the age difference is not that big between us, okay? So I missed out on something over these years, but anyway, at that time, I realized that this was not a boundary. So what's left to say? Well, still my logic is very limited, so I'm only using Boolean expressions. He's an aspiring teacher, an incredible supporter, a creative host, a warm-hearted friend, and that makes a wonderful person. Thank you very much.
All right, it's my pleasure to introduce our last speaker before we get to hear from our distinguished guest himself. And it is rare that I get to watch movies and see my former students' names on them, and I still get a thrill every time I see a Pixar movie and I get to see Danielle Feinberg's name as director of lighting or whatever. And she's also been a great source of inspiration for my young daughter when I can say, that was one of my students, and she's doing all this cool stuff. So Danielle, take it away.
Okay. You may have noticed I'm limping. Margot misunderstood the expression twisting your arm, and she twisted my leg to get me here. No. So today I would like to talk about a few things that I learned at Harvard. And so I grew up in Boulder, Colorado, and attended a somewhat mediocre public high school, and thought that I had worked quite hard to in my sort of academic career there, and one day I got into Harvard, and I thought this was the most amazing thing that had happened. And I got to Harvard, and what I learned was what hard work really meant. And so I arrived on campus thinking I was going to do mechanical engineering, and then I looked at the list of classes and thought, no, I'm not doing mechanical engineering anymore. And I don't like the sound of those classes, but the sound of the classes I really like are these computer science ones, and they'll count until I can figure out what kind of engineering or whatever I'm going to do. And I had been programming since 4th grade. I started with the Logo Turtle, if anyone's familiar, where you write code and it draws pictures. You notice I work at Pixar, so that may have been fortuitous. And so I had been programming, but not in a hardcore kind of way, in a making pictures kind of way. And I loved programming, but it was sort of like this hobby, and it had never occurred to me to major in computer science until it took me all of 2 weeks into CS50 to go, oh, duh, why am I not going to major in computer science? This is something I love. And so off I went, and I worked hard in CS50, and then I was rewarded with many long nights in the Science Center and in my dorm room. But then I got to CS51 with Harry Lewis, and then I really learned what working hard was. And CS51, I don't know if there's anyone in this room that hasn't taken it, but it was sort of the weed out class for computer science at that time, much more like organic chemistry was for the whole rest of the school that wanted to be doctors. And so, but you knew if you had worked hard and survived CS51 and you still loved programming, then you had probably made a good choice, was how I felt about it. And the problem was that it was a lot of work, and I found myself staying up all night at least 1 to 3 nights a week. And so I was in Strauss C, and all I had to do was look out my window and see the corner store there that here is not 7-Eleven, but I can't remember, whatever it is. And it beckoned to me on those late nights. And so this is how I got through those long nights. Was I'd buy a 6 packs of the powdered sugar donuts and a can of Mountain Dew, and I'm not sure how many years of my life I dismissed eating these things, but it really got me through those long nights. Now the problem was I also played softball for Harvard. Here's a particularly bad picture of me doing it. It looks like I'm enjoying myself quite a lot. So the problem with playing softball in Boston is that the weather is terrible. And so you have to fit your entire season into like 5 weeks, which meant we played 8 games a week. Now, this being Harvard, I know you're doing some math and saying there's only 7 days in the week. We would play a doubleheader on Tuesday, Thursday, Saturday, and Sunday. So I was doing that and staying up 1 to 3 nights a week for CS 51, and then the softball team was nice enough to have at least 1 kegger a week, which I was a freshman, of course, I was taking place in that. And so this is, this is where I truly learned about working hard. It somehow was actually my best year in softball, I think, because it like actually shut my brain off because I was a complete zombie, but that's probably a different story. So I learned how to work hard, but there's sort of a subset to this too, which is when I arrived as a freshman, I'm trying to figure out how to manage this whole workload thing and this being away from home and school. And I decided to add on top of that getting a job. Not for the good reasons that normally come with that, but I had a boyfriend at the time who lived in Illinois, and I thought, I sort of did this calculation with the critical thinking that got me to Harvard, which was, if I worked a job for maybe like a month, I could make enough money to buy a bus ticket, because bus tickets are cheaper than plane tickets. And I could get to Illinois in time for Thanksgiving. So the important thing was to find the best paying job so I could work the least amount of time possible so I could get back to all my homework. And so I did a lot of research, which involves, I think, looking at flyers on posts. And it's possible you shouldn't take the job that advertises the most, but I did, and I ended up working for Dorm Crew, which is cleaning the bathrooms in the dorms. And it paid really well. And I went in, and of course they were happy to give me the job. And, but they said, well, there's just one thing. We only have one dorm available right now, and it's your dorm. And so all of the people in my dorm, my first semester freshman year, thought I was the girl that cleaned the bathrooms. Now, as you can see by this current picture of Dorm Crew, this is a very popular job. I was quite excited by this, much like the guys in this picture at that level. And even when I did it, we didn't even have these nice backpack vacuums. That must be a new thing, so extra exciting. And so this is where I learned the lesson that you work hard, but try to work hard on the right thing. And so around this time, one of my teammates on the softball team, who was an upperclassman, got wind of what I was doing working in Dorm Crew. Now, this woman ended up being my first girlfriend later down the line, but that's another thing I learned at Harvard, but that's probably a different story for a different time. So this idea of work hard on the right thing, she says, you're quitting Dorm Crew, and I'm getting you a job in Harvard University Mail Services. And so she marched me down to the Dorm Crew office to make me quit. And so I told them, I'm really sorry, but I have to quit. And they said, you can't quit. We're giving you a promotion. And it became clear to me very fast, I might have been the only one actually cleaning the bathrooms for real in Dorm Crew, because I worked hard at whatever I put my mind to. And I want you to spend just a second thinking about what a bathroom for freshmen might be looking like, away from home for the first time. Anyway, so I left that job. I turned down the promotion, of course, and I went to the Harvard University Mail Services, which was a fabulous job and paid just as well and was infinitely less disgusting, and came with my boss, who was a lady named Shirley, who started every sentence with, ah, shoot, or really probably more like, ah, shit. And she would regale us with stories of her weekend bingo wins and things like that. And so I learned some very important lessons here that carried well into my career at Pixar, which is obviously this sort of hard work and perseverance spent on something that you really love. I worked my butt off at Pixar, and I started in this very entry-level technical position doing rendering. And so I was doing coding there, but it wasn't anything that showed up concretely in the movies. It was more like scheduling renders and things like that. But I kept working hard, and it was a really magical time then where no one had any experience. And so at the end of my first movie, A Bug's Life, they said, well, what would you like to do? And you could sort of choose where you wanted to go. So I said, oh, I'd like to try modeling and lighting. And so off I went to figure those out. So on Monsters Incorporated, I don't know if any of you have seen it. This was, Margot has, okay. Oh, nice. This is very exciting because this was actually the first code that I wrote that generated visuals in a movie. And so It was a simple piece of code, but it was some sine waves and some randomization and some artistic controls to make the leaves on this tree outside the window flap in the wind. And this was also a lesson from me that you can put a lot of work into something and no one will ever notice. That shot just keeps going and going and going. Okay, so the next thing I learned at Harvard was about barriers. And there's some very concrete barriers, like when my softball teammates took me to the Crimson Bar and Grill, insisting anyone can get into this bar, you just have to have any kind of ID. So they hand me an ID, they all go in, and I hand my ID to the bouncer. And it turns out that everyone doesn't get into the Crimson Bar and Grill, especially when the ID says that you're 28 and 5'9". So that ID had been handed down for an inappropriate number of years. And I discovered that that was a real barrier. When I started at Harvard, I understood that there were some other things that were more like perceived barriers. And so one of the most amazing things to me when I stepped on this campus was meeting other freshmen and learning that they had done things like the guy upstairs had started this public service sort of group in his community that had made huge strides, and he was just a freshman coming in. And then people who were doing groundbreaking science work and outreach in other countries, and all of these things that I thought were reserved for adults, not kids. And so it was this real lesson to me about how to live life bigger and more boldly. You know, when I was in high school, all I was doing was trying to work on my, getting good grades and SATs and playing sports and extracurriculars. And I was trying to figure out how to kind of make the nerdy, cool thing work out. So I'm still working on that. But all of these things with the barriers really comes into play at Pixar because having been there for 20 years, there's a lot of barriers that we've hit where we get to a movie like this is The Incredibles, and we had a director who it was his first movie at Pixar, and he had only ever done hand-drawn animation before, and so we storyboard the movie out first, so it's quick gesture drawings. And he drew out the scene, where the mother tucks Violet's hair behind her ear. She has this nice, long, flowing black hair. And if you're going to draw that, it's no big deal. He looked at the room, and all the technical people in the room had turned sort of pale white. And he's like, well, what's the problem? And they said, well, like long hair is an unsolved problem. We don't know how to do that. And tucking it behind her ear, are you kidding me? And he thought, well, like, these people are crazy. Like, what do you mean that's hard? And so he then went on to explain that this is a really important part of the story. This is a story point where the daughter's name is Violet, like a shrinking violet. She hides behind her hair. And in this moment where mom tucks it behind her ear, it's our sign to the audience and to everyone that she's sort of emerging from her shell and she's going to use her superpowers. And the wonderful thing about Pixar is there's this real guiding principle about story. And so it doesn't matter what it is. If it's a story point, then we figure out how to do it. And so we drive technology that way, and it doesn't give you the luxury of saying, we don't know how to do that, or we don't have enough money to do that. It's like just get down to brass tacks and figure out how to do it. And it's something that has made me utterly love that place. And so here's the scene that resulted in it. Maybe a little bright in here to see too much.
You'll know what to do.
So, but we're not stupid after all. This lady right here was supposed to have long hair too, but it wasn't a story point. So we gave her this really nice asymmetrical 80s do. Okay, so another thing that I learned in my time at Harvard was the power of technology. So as James was saying, we were here at about the same time, and it's like you come in, you don't even have email, and there's no such thing as the internet. I remember my first peek at the internet in the Science Center, and it was like some weird text on a screen, and Professor Joe Marks is telling me like, no, you could probably find a job this way. And I was like, yeah, right, dude, I don't know what you're talking about. And then by the time we leave, we all have email, and the houses are all wired up, and I'm writing a website for the softball team. And it was sort of like, back then it felt a little bit like computer science might open 10 or 100 doors, whereas now it's opening thousands of doors. And so you were only getting sort of little glimpses of what it could do. And so as another little glimpse, going back to my Harvard University mail service days, I had been working there for a little while, and somehow I saw how they were doing payroll. And I said, hey, I was rather horrified, and so I said, I could probably help you with that. And they were, what? I don't know what you're talking about. I said, well, let me just do this. And so I'm going to, let's say, programmed an Excel spreadsheet for them. It was like the simplest programming I had ever done. But, you know, for them, it was like I was the second coming, or I guess the first coming of like the Postal Service God or something like that. I don't know. It was like the guy who did payroll, it was like his whole life had changed. And so I got a raise, and now I was making more than I made at dorm crew. And so in celebration, I had been messing around in my spare time with, I don't know if anyone remembers ResEdit, where you could kind of hack into Mac things. And so there was a screensaver, the flying toaster screensaver. Does anyone remember that? And so I was hacking the images in my spare time, and so I made Hums a screensaver that had the little mailbox flying by with wings and had Shirley saying, "Oh shoot, as she flew by. And you know, this time period was when, with the Excel spreadsheet and the raise and the screensavers, I thought to myself, this technology thing might really get me somewhere. So for the power of technology, I get to witness this all the time in my work, and it's really quite wonderful from where I am. I work on the films for about 3 years now, and I'm at the sort of beginning stages where we're deciding what technology we need to develop for each film, and being in the middle of seeing those advancements and getting to help drive some of that. And so Brave was an interesting one where it's taking place in Scotland in the Scottish forest, and we've really felt like it needed to be this nice, lush, rich forest. And so we're looking at the artwork to get a sense of it. Maybe if we could dim the lights, if that would work. So these giant wide vistas and all of the wonderful sort of mist and weather that you get in Scotland. And then we're getting these wonderful paintings of the forest. And then we're getting these sort of more and more worrisome paintings where there's more and more detail, which means more and more things the computer has to compute. And then we get these photos from the research trip, and you can see all of this beautiful landscape and all the different vegetation and different grasses and mosses. And then we start getting reference from the art department like this. You can see this is photo reference too. I think there are about 20 more of these, and it was all about the different kinds of moss. And then we're getting these little vignettes of how this vegetation should go together. I know so much more about Scottish vegetation than I really ever expected to. If anyone has any questions, I'll be available later. And then we find out that the art department is making Photoshop brushes of lichen, and then they made more. And so we knew that we were all kind of in some serious trouble. So the movie we had made most recently before this was Up, and this is a stylized movie, so everything's sort of on a bigger scale, but this gives you a sense of where we're going. So here is Up, and here's where we had to get to. And so the level of detail was on a completely different order than we had done before. This coupled with the movie Avatar had come out, and this feeling of you always have to sort of keep up with the Joneses, and Avatar was such a lush, rich world that we felt like if we didn't at least come close to that, people wouldn't really buy into the world in the same way. And so what this meant in the wonderful times of innovation is you have to throw out everything you've done before and come up with a totally different way of doing things, which is the scariest but always the most exciting too. And so we came up with something that got dubbed Wonder Moss. It was originally just going to be used for the moss, but was so successful we used it for almost all our vegetation. So one of the problems is we need a ton of geometry. One of the cheapest things you can give the computer is just a curve. And so the first layer of this is growing curves on the geometry. So you can see we're doing grass and leaves and bushes and all kinds of things. And all of this is just generated by math at render time. It was done by this wonderful guy who, when he looks at nature, he sees math, where most of our artists have a couple math equations they can use to kind of do randomizations to make things organic. And he sort of sees it in the flip way. So the first thing is growing curve. I know you're looking at this and you're like, yeah, not impressed yet. So we grow curves, and then we turn on the next part of Wonder Moss, and it does this thing he called enveloping, which is sort of the bumping and clumping to get things to look more organic. And then we turn on gravity, and this is really all just in the mathematics of the curve, so very cheap still computationally, which is important for how much stuff we had to get on the screen. And then, of course, because we're doing vegetation, color becomes a very important part of sort of the history of vegetation, of what's fresh and what's old, In the computer, you can make the mistake of everything look like it's brand new. So we have to kind of build history into things. So again, it's a more believable world. And then this is my favorite one. It's called extra curve variation. And you can't see it in this one very well, but there's little flowers growing in the grass. So I'll show you, this is an early development loop. And you can see here in a second that all of these clover are going to grow in certain patches on the tree. And the wonderful thing about this is the part of the code that's sort of adding the little oddities and spice of life that makes nature. And so what this is doing is calculating where the divots in the tree are with the idea that they would get less sun, they would be more damp, and that would be where the clover grows. We use this same kind of ideas and process on clumps of needles, so the newer needles versus the older needles, or having the flowers grow in certain places, or having this procedural wind that we turn on here in this next one only activate in certain places. So all of this is math that's getting all of this incredible organic nature into our movie. Now, most of the time when we use the power of the computer to generate our stuff for our movies, it only gets us part of the way there. What we really need is systems where we harness the power of the computer but allow the artist to have as much control as possible, because they can't be unlinked, or you end up with very sort of artificial looking things. And what we want is this sort of rich world that you can immerse yourself in. This is the example at Pixar that went the furthest I have ever seen. It probably was like 90% successful in all cases and making it just look outstanding. The wonderful thing is that the engineer still went the extra mile and built everything in so that an artist can do whatever they want on top of this. And so if you need a path for Merida and her horse to walk down, you just paint in a path and the grass grows shorter there. Or if you don't like the clover where they grow, you can easily take it away. And so it was this magical combination of the two, so we had the best of both worlds. And so in the end, we end up with a forest with all of this detail. But we can change it around depending on the vegetation and get all these sort of different types of Scottish landscape by the castle, or by the river and sort of changing the color of things, or up in the Scottish Highlands. And so here's a scene from the movie, a shot in the movie, and this is how it looks coming into lighting. So this is coming into the department that I do. And once we get our lighting in there to set the mood, you can see how much it changes and maybe why I've fallen in love with lighting. And so this was this wonderful example of sort of heavy technology with the ability to do the art. But it's always a balancing act for us. And so WALL-E is this very interesting example of that, where when we got into making WALL-E, the people doing WALL-E's eyes got super, super geeked out about it. And they're like, we're going to make these like practically optically perfect lenses. And they studied camera lenses and all of the optics and got it just right. And then we went to light it, and what happened was WALL-E looked completely glassy-eyed. And so I don't know how many of you have seen WALL-E, but this is a movie about a robot who it's a movie about a robot that we have to believe has a soul and a character and can fall in love. And so glassy-eyed is kind of the antithesis of that. So we knew we had a real problem on our hands. The other thing is that WALL-E doesn't have any traditional dialogue, and so the animators are really stuck with very few things for him to act with. So the binoculars are a really critical piece of that. He has his little eyebrow flaps, and otherwise it's just his body. He doesn't have a mouth or a lot of things to express with. So those binoculars are a critical piece of his acting. So it was really important that we got him right. So we went in to try and figure out how were we going to solve this problem we kind of got worked into by the technology, where we couldn't actually address the story correctly with the eyes the way they were. So you can see WALL-E has 3 lenses here. Here's the front flat lens, and then he has a concave and a convex lens in there. So when we put all the reflections on, you can see it's definitely very glassy-eyed. We tried actually a lot of sort of stupid things that would have been sort of easy to pull off, where we faked sort of blocking the reflection in there, but it looked very fake and distracting, or just turning it down, but then it doesn't actually look like the materials of binoculars. You know, the last thing we want is for it to look like we put googly eyes on WALL-E. It would have looked really stupid. And again, we never want to pull the audience out of the movie, and so we kept working on it. The other problem was there were times in the movie where we actually had to see something reflected in his lenses, and so usually it's Eve. And we, you know, as he's falling in love with her, we understand that he's looking at her. Now, but in this image, we have controlled it so Eve is only reflecting on the front lens. and it's already glassy enough. And then we put Eve on the second lens, and you can see it's getting worse. If we put her on the third lens, she'd actually be upside down, which is even worse. So we're really kind of backed into a corner. So we still are working on things. We turn the reflection down. And then this is sort of the magic moment here. I don't know, can you guys see that? I know it's really subtle. But what happened was the lighting artist that I had working on this added a light to WALL-E, but messed up the shadowing, which means the light leaks inside the binoculars. Because the inside of the binoculars are black for the most part, it doesn't show up. But it hit the aperture blades inside there, which are gray. And what happens is that cuts through the reflection more so than anything else does. And so what we begin to see is we still have the reflection like it's a piece of glass, but we start to see what's recognizable as an eye. Because as the human, we have the white of our eye, the colored iris, and the black pupil. And suddenly WALL-E has the black of the sclera and then the gray iris and a black pupil, but we maintain that reflection so we kind of get the best of both worlds. So it ends up being this serendipitous thing that sort of pulled this all together. And so we have this moment where we figure out to do this, but then the really cool thing is that when we get to this last scene in the movie where, I hope this isn't a spoiler for anyone, but where WALL-E sort of dies and loses his personality, the perfect thing is to make him glassy-eyed, and so we take that light away, and we end up with glassy-eyed WALL-E feeling like he has no personality. And then, once he comes back to life, we add that light back in, and the animators made him look wide-eyed and like a puppy dog, sort of, and so we get all the best of WALL-E back, and he returns to that sweet, soulful robot that we have come to love. And so while I learned about the power of technology at Harvard, at Pixar, I've really learned about the power of technology and art together to create something bigger and better than either of them alone. If you will allow me, Harry Lewis reminds me a little of WALL-E. Because it's nothing about the glasses. WALL-E is this guy who searches through the garbage dump and he finds the little cast-offs and they're his treasures. And so I think of him as kind of the guy who finds beauty and value in what others ignore or cast off. I learned all these great things at Harvard that I've talked about, working hard, ignoring barriers, and how powerful technology can be. I also got to take amazing classes and get an amazing education, and was encouraged to be much bolder and bigger in my life decisions. But the most important lesson I learned at Harvard was from Harry Lewis, the one that has had a direct impact on me every single day. Like WALL-E, finding the value in what others would ignore or cast off. In a room where, as a woman, there were only 10% of the people that looked like me, he treated me like I deserved to be there. That is the most powerful and lasting gift you can give. Thank you, Harry.
So before I launch into my thank yous, and I won't hold you, I hope, too long, but I've got to, first of all, explain what is going on here today, okay? So this is, in fact, my 70th birthday. This is a celebration of computer science at Harvard. And I'm going to come back to what I really think we're celebrating about computer science at Harvard at the end of this. But what is happening is that I have announced that I am going to retire someday, okay? I am like not retiring tonight or anything like that. And as as one of my former students emailed me, he said, I thought Harvard professors never retired. It's just that Harvard stops paying them after a certain point. So yes, the point at which Harvard stops paying me is a few years out. But and as Cliff said, the next 2 years, I'm going to be teaching a paper on a class on the 50 classic papers of computer science that every computer science student should have read if they're going to be called a computer scientist. So that's going to be super fun for me for all the reasons that I think you can integrate from the talks that have come today. I'm interested in all different aspects of computer science and lots of things that aren't computer science, and I do believe everybody should know some history. So that's what we're celebrating. We're celebrating a phase transition for me, and we're celebrating computer science at Harvard.
So I really can't tell you how much it means to have so many of you here from the 5 different decades in which I've taught here. And you know, if I thanked everybody, we'd be here all night. And I think some people are not going to last all night. So please trust me that if I don't mention you specifically, I love you also. So first of all, I want to thank my students who have so willingly cooperated in creating the illusion that I know how to teach. It's an old saw that you learn more from your students than what we teach them, but it's certainly true in my case. I never had a proper education in computer science. The field barely existed when I started in 1974 on the faculty, and Harvard's program was not all that strong. I actually switched from systems to theory in the middle of grad school because I'd been married for 5 years by that time, and I wanted to finish fast. That's the only reason I'm a theorist. It's honest and true. I mean, so just let me just give you the quick bio. So I worked in computer graphics as an undergraduate after actually being driven out of math by Math 55 at the time. Like, how many people were driven out of math by taking Math 55? I love it. I love it. The math department has done more to create computer science than it has any idea. And then I was in physics for a year until I completely screwed up a lab experiment. You know, I divided 10 plus or minus 5% by 2 plus or minus 5% and got 5 plus or minus 5%, which seemed to me like the right answer, but wasn't. And so then I moved into computer science after I basically lied myself into a programming job on a mini computer. And and I worked with Ivan Sutherland, who was in computer graphics, and left for 2 years to do national service. I was at NIH as a commissioned officer, traveled for a year in Europe, came back and started graduate school, and have been here ever since. So that's the quick bio. But in graduate school, I really did notice that all the systems students seemed to have gray hair because they were too valuable to be allowed to graduate. And I wanted to finish quickly, and I discovered that I could publish theory papers, and people thought it was wonderful. And I, unlike Eric Roberts, did not grow up wanting to be a college professor. I had no concept of being a college professor. My parents were doctors. My older brother, who's here today with us, is a physician. I knew I didn't want to do that, but I respected it. Just I knew it wasn't me, and I just figured I was going to go into industry. But the job was there at Harvard, and I got it. My wife was in graduate school by that time, so I didn't want to leave Cambridge. And one thing led to another, and I've been at Harvard my entire career. When whoever it was who brought up the Stewart brought up the Q Guide rating from 1974, I had taught that graduate seminar that Guy Steele talked about. And then I walked into a classroom of 350 people in Science Center B to teach NatSci 110, a course that existed already, so I had somebody else's notes to work from. But that was my first teaching experience. So I've counted on generations of smart freshmen to teach me what I need to know about computer science. And there are some who taught me other things. So I want to just give you a flavor of what I think I've learned from my students. So I want to give a nod to the woman I taught in AM 110, which is what CS51 used to be called, the course Danielle talked about, around 1980, who told me at a house dinner that she would be giving a piano recital in a few days. I didn't realize at the time she said that she was going to be giving the recital in Carnegie Hall. And so just making conversation, I asked her if she practiced the piano every day. And she said, well, I did practice every day from when I was 4 years old until assignment 7 was due. For those who remember the old AM 110, that was the garbage collector. Which is really hard to write in assembly language with no debugging tools or anything like this to speak of. So I I'm not sure that conversation made me kinder. I like to think I've always been kind, but it did make me a little gentler. Then there was the guy who introduced me to his boyfriend a few years ago, and not anybody I remembered, and he thanked me, and not for anything I taught him in computer science, but for pausing in the middle of my proof of the recursive undecidability of the Entscheidungs problem to describe the tragedy of Alan Turing's life. And it was, he said, the first time he felt at home at Harvard. And, so it's a lesson for all of you who are, whatever your walk of life, the lesson in the importance of, small human stories interspersed with whatever more serious or more professional work we're doing. There are lots of other students who've taught me about differences, and it's one of the great privileges being at Harvard to be in the middle of such a genuinely diverse community. There was the German student, not Christoph, who informed me after a midterm exam in a programming course that required making a data structure for balls and strikes, that baseball was not actually intuitive to all human beings from the time they were born. Learned a little bit about cultural sensitivity there. Or more seriously, I had a Pakistani student who explained, after I gave some probability homework that involved poker hands, that Muslim girls raised in conservative households did not actually learn about aces, clubs, and jacks. So, and I've got to give a shout out to a few people who aren't here to hear them. There was the brilliant Julia Schaffner, whom Michael Mitzenmacher will remember if Michael's still here. I think he was her classmate, and maybe classmate of a few others here. Yeah, TF'd with Ted, I think. She was an undergraduate TF of mine in 1980 who taught me the art of compromise and commitment. So after a bloody battle in a TF meeting, Julia and I agreed that I would be allowed to continue calling the traveling salesman problem by that name as long as I went on to say, whenever I explained this, that it was but a special case of the more general traveling salesperson problem. And those of you who've taken CS 121 in the days since then know that I have kept true to that promise to Julia, even now, more than 20 years after she passed away far too young. So anyway, and I've just got to mention one other, totally riveting memory of what interesting people you have in your class. So I went and I was teaching context-free language theory in CS 121, and I talking about Chomsky normal forms and the general grammar context-free recognition algorithms and stuff like this, and and we go into staff meeting, and I just sort of take this. I always try to take the temperature of the class by talking to my TFs, and and one of them said, yeah, Harry was really into that when you were talking about it, and I said, Harry who? And they said, oh, Harry Chomsky. You didn't know that Harry Chomsky was in the class? They said, no, I didn't know that Chomsky's son was actually learning about Chomsky normal forms from me, and I was glad that I didn't lapse off too much into narratives about that. So I've got to thank everybody who's taught me. Remember, I'm not going to have a retirement party, so I got to do the whole retirement party thing here. Ivan Sutherland, Sheila Greybach, Bert Drebin, each of whom made a lasting impression on me in a different way. And especially, again, I got to give a shout to Doris Aronson, who's a person that probably none of you have ever heard of, psychology professor at NYU. She was here at Harvard when I was an undergraduate, who let me get away with murder in an independent study my senior spring. And had she failed me in my independent study, which she certainly should have done since I did absolutely nothing for it, my entire life would have collapsed, seriously, because there was the Vietnam draft there hanging over my head, and I couldn't get that commission without a college degree. So she agreed to pass me if I would return all of the books that she had lent me at the beginning of the term. So my entire teaching career, it's been very hard for me to be mean to any student with that memory lodged in the back of my brain. People were good to you, so you should be good to them. So. I want to thank my old school, Roxbury Latin, of which Larry Lebowitz and Dick Lewis are also graduates, for a peculiar reason. They may not know what I'm going to say here. it was there that I learned that brilliance and weirdness were not inconsistent. Rebecca Nesson talked about my appreciation of oddballs. Well, the faculty was a collection of oddballs there. But it was a structured environment, a highly structured environment that actually acknowledged and protected a great deal of freedom of operation. And that is a general theory I have about freedom and creativity. You know, I learned to act there at Roxbury Latin. I was on the stage a lot. I used to, like my brother, give orate in Latin and so on. And you know, I firmly believe that while you actually have to, on one-on-one conversations with students, you have to make a personal connection. You have to have empathy and understand where the student is coming from. But nobody wants authenticity from the lecture hall, right? People want performance in lectures. And playing Henry IV was a very good preparation for being a Harvard professor. I think that's the reason why I could walk into Nats I 110 in 1985 and act like I knew what I was doing, because I was good at acting. But as I say, mostly I learned that a great faculty, this is the enduring lesson for me, a great faculty resembles the Star Wars cantina, with people, you know, tooting horns and with slimy brains exposed, and, you know, drinking dangerous drinks and going on dangerous missions. So speaking of the Star Wars cantina, I really want to thank my colleagues in the Harvard Computer Science program here. They are an assortment of oddballs assembled from across the galaxies, but they are the best. You are the best, and I do appreciate and will continue to appreciate being able to work with you. And of course, especially the 7 of you who actually I had as students, and the 6 of you among those who were my teaching assistants. Henry Leitner, Stuart Schieber, Margot Seltzer, Michael Mitzenmacher, Salil Vedan, David Malin, and Sasha Rush. So I'm going to mention 2 others by name. Deborah Abel, I don't know if Deborah is still here. She got a shout earlier today from somewhere. So Deborah is my long-suffering teaching assistant. She's basically been my teaching assistant almost every term since 1999. She still is running the extension school program versions of my courses. And Eric Roberts, who I think still is here somewhere, right? Did Eric leave? Yeah, there he is. Okay. So Eric Roberts, I just, you know, again, those of you who are in the field know this already. Those of you who are not on the field should know that Eric Roberts is, as Tom Lehrer would say, the greatest who ever got chalk on his coat, right? He is the best. And as someone who knew absolutely nothing about teaching, when I walked into this enormous course in the fall of 1975, I had the good fortune to have Eric Roberts as one of my teaching fellows. And Eric himself had been a teaching fellow for Bill Bossert and Chuck Prenner when they taught the course. And I just did whatever Eric told me to do, and I've been continued to do that ever since. Of course, Margot, most of all, you know, thanks for putting on this wonderful day. She was my TF in the fall of 1982 when she was a senior already, I think, in college. And I think it was not very long after that that I started thinking she should be a professor here. It took a decade before that happened, but if I had anything to do with bringing her back to Harvard, I think I've repaid all of my debts to the university by that one act. So not to spend too much time on it, but can we all please just agree that I have the best family there ever was? Okay? To my brother Dick, thank you for providing the sibling rivalry that made me study harder, and for the love that shows that there was no winning and losing between brothers, and for the work to which you've devoted your life to save people's sight. Dick actually saw an article about me when I was dean in Harvard Magazine, and it included a nice picture of me working on a computer, and he called me up, not to congratulate me, but to say, dude, get new glasses. You know, I'm surprised he didn't give me the prescription, you know, there over the telephone, just by watching the angle at which I was holding my head here. Dick, for those of you who know what my office looks like, is the neat brother. He's the one that you want doing retinal surgery on you, okay? And as to the family that I had something to do with building, what a deal I've had. Nothing that has been talked about today, nothing that's happened in my entire professional career would have happened had I not fallen in love at a young age and had Marlon not insanely agreed at age 19 to marry me. So she's been my support and my soul for every step of the way, and for the past 30 years, also the supplier of the incredible students I have had the privilege to teach. So thank you for that. Although there were moments during my 8 years of dean of the college when I would come home from ad board meetings and, you know, roll over in bed with Marlon and say, "What idiot let that person in?" And she would usually say, "It was a faculty case," okay? One of the best things about stepping back is that I hopefully will get to spend more time with her. Elizabeth, thank you for putting up with all the crazy people we had taking care of you while your mother and father were working back in the days before the terms parental leave and professional child care had even been coined. I'm told that it is the reason why both my daughters have such good social skills is because they so early learned to manipulate all of the crazy people who were their caretakers. Annie, thank you very much for the Larry Summers dollar bill you gave me in the fall of 2003, which you kindly asked the great man to autograph for me at your freshman barbecue. She shows up at my office door with this thing, and I just say, "No, you didn't do that, did you?" Okay, with kids like that, how bad can life ever be, So, and to Annie Elizabeth both, thank you for knowing everything and saying nothing all those years. You learn a lot by sitting around the dinner table every night with Harry and Marlon. And while I have the microphone, can we thank Elizabeth for bringing David Farenthold into the family? For those who don't know, Dave just won the Pulitzer Prize for his reporting on Trump's charitable non-giving and for breaking the Access Hollywood video story. If anyone, by the way, this is a big group here, if anybody has Trump's tax returns by any chance, I'm sure Dave would be delighted to meet you. And finally, I want to thank Harvard for letting me get away with this scam all these years. What I mean is, the privilege of teaching stuff that I actually don't know much about. I think what we are really celebrating today is, yes, computer science at Harvard, and yes, my 70th birthday, and yes, the fact that Harvard is breathing a sigh of relief that I really will go away at some point. But, I think we're celebrating the twilight of the amateur era in computer science. I started I taught CS51. That course existed, but it changed a lot while I was teaching it, as it's changed a lot under every subsequent teacher. And then all of these other courses that are now in the backbone of the curriculum, CS121, CS50, CS124, the algorithms course, the BITS course is now come and gone, but the gen ed course that I taught with Hal Abelson, whom I'm happy to see here on the social dimensions of the information revolution, CS20, and now this classics course that I'll be starting next year. So none of those courses exist. It's been about 30 years since I taught a course that I didn't start, and I created these courses just because they needed to be taught, not because they were what I knew And I've always thought the job of the professor was to teach what needed to be taught rather than teach what the professor knows. And so I'm the product of a lot of on-the-job training. I learned computer science by doing it as an undergraduate in Ivan Sutherland's lab, as a public health officer, keeping the computers running at NIH, in a not very good grad school program here by jumping around among topics, looking for the fastest way to finish my dissertation, and as faculty came and went, and as a faculty member by deciding to teach courses because they didn't exist and I knew what students needed to know, even if I didn't know it myself. So some of you know that in addition to the computer science courses I have taught, I regularly teach a course on athletic amateurism. It's a freshman seminar. It's a fun subject to teach because I like sports, I like Harvard history, and the history of collegiate sports has a lot to do with Harvard history. I like freshmen. I like the Harvard archives, which we use extensively in the course, and for lots of other reasons. But those who've taken the seminar know that amateurism is not all that it's cracked up to be. The amateurism rules in sports were actually constructed to protect the British upper classes from having to compete against people who were stronger and faster than they were because they had worked with their hands, because the working classes had worked with their hands and they were better athletes. And the amateurism rules that you couldn't take money for sports and be a real sportsman were designed to exclude the people who didn't have any money. So amateurism is kind of a tainted concept, and that's part of the lessons of my amateurism seminar. But I still think the concept has some nobility to it. It's an important idea that we can strive to do things at a high level because we love them, even though we have no professional training in them. That the key ingredient in excellence in anything is our own passion for it. And I'm very glad that we are past the amateur era in Harvard computer science. That is something that I was a product of, and I'm glad we're not passing along to the next generation a faculty consisting of amateurs. I've loved being part of it, but I'm glad that that day is gone, and I think it's pretty much gone from the entire field of computer science. And so I think this occasion, I think, is not just a celebration of computer science, but a celebration of the end of the amateur era. But having said that, I hope that the love and the joy and the fun with which I've experienced the field will never die here. Thank you.
I'm Henry Leichner. I'm very happy to have had Harry as a friend, as a mentor, as a teacher, as a colleague. But as Margot mentioned, there were a couple of Harry's former students who really, really, really wanted to be here, but were unable to come in person. And so, let us start first. Yeah, maybe dim the lights a bit.
Happy 70th birthday, Harry. You've done amazing work at Harvard with the computer science department, with the undergraduates. All your work has really contributed to incredible success of the students that have been there. I certainly benefited from your support, so I have a lot to thank you for, and hope you have a great birthday and continue your amazing work.
Footnote to that, Harry, as you know, I and Bill and Guy Steele were all in that early class of yours. And I think there was somebody else who was interested in saying a word here, so bear with me.
Happy birthday, Harry, and congratulations on your retirement. I will always remember my first lecture with you because it was my first college lecture ever. I was running late to Computer Science 121 after staying up all night coding, so I threw on a t-shirt and didn't realize until afterwards that it was inside out and backwards with a tag sticking out the front. I couldn't figure out why no one would talk to me. But eventually I got my shirt turned around and your class became one of my favorites at Harvard. Small sample size, but still. In fact, not many people know this, but after taking your class, I built a website that pulled stories from the Crimson Archives and linked people whose names appeared in the same news story. Your name ended up being the one most people had in common, so I decided to name it 6 Degrees of Harry Lewis. I remember emailing the idea to you and asking your permission, and you said something like, "Sure, what the hell, seems harmless." To me, that story speaks to the kind of teacher you are and the way you inspire your students to experiment and build something new, as long as it seems harmless. So Harry, today I want to say thanks for encouraging me and thousands of other students who have been lucky enough to get to know you. Great teachers never get enough recognition, and you've always been one of the best. So I hope you have a very happy birthday and a well-deserved retirement.
And I thought perhaps we would enter the reception with a little bit of a musical interlude. You'll get the idea in just a moment. It's short and sweet. I'd like us all to sing a ballad of a true great Harvard sage. His name is Harry Lewis, and he's just not over age. A brilliant polymath and writer, a man who speaks veritas to power. His truth goes marching on. Glory, Harry Lewis. Glory, 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 Harry Lewis. His truth goes shining.